can get very confusing if you never sort of have a little bit of an explanation presented. And then we'll look at hardware. As I said, we'll look at molecular dynamics, practical, and then Holly will talk about later about some of the ways that actually essentially about MPI and OpenMP, these programming terms, parallel programming terms you've heard being used. And as I said yesterday, the course isn't here to teach you how to program in parallel, but it's useful to understand how these things are done in software, so that when you use software, as I said, if you read manuals, you'll still come across terms like MPI, OpenMP, processes, threads. So and if you're using an HPC machine, it's important to kind of know at least be aware these exist and kind of have a rough idea of what these terms mean, so that you'll be better equipped to use HPC machines and HPC software. You already compiled software yesterday. I got you to compile Hammer. That may be completely commonplace for you. You may be very used to doing that all the time. You may know everything that's involved with compilation. But if not, this should be a useful session later today, talking about what compilation actually does, why we need to, why it's useful to know about. So that will hopefully be useful for people who have less experience or knowledge of that. Okay. So with that, I'll hand over to Julian to talk about measuring parallel performance.
Thanks, Arno. Sorry, 1 second to share my screen. I hope everyone's doing well and had a good evening after yesterday, and that everyone's looking forward to today's session. We're going to start off thinking about performance, how to measure performance, and what it means for code to perform well, scale well, and that sort of thing. So let me start off as well, just to make sure what you're all thinking about. Oh, thanks, Arno. So to start off with, could I ask you all in the course Etherpad to write down why do you think that running applications in parallel is useful? Like over the past day or so, we've been talking a lot about. I plunked things in the wrong chat. Thanks very much, Arno. Over the last day, we've been talking a lot about running in parallel and how HPC is good for running in parallel. So I'd be quite interested to see in the course Etherpad, why do we bother running in parallel? So the couple of answers so far are efficiency, speed and efficiencies to speed up the calculations, and either shortening the computational time or running multiple projects at once. All of those are entirely sensible and accurate reasons. And indeed, there are usually two advantages to running applications in parallel. One is that hopefully applications will run more quickly, and then we can get our solution faster. But also the second one is we can solve larger, more complex problems. So actually, very few of the answers touched on that, but I'm aware that a lot of you are molecular dynamicists. The very early papers in molecular dynamics were looking at maybe around 128 to 256 total particles. Whereas now, like yesterday, we had someone talking about 100,000 atom systems. So there's been a definite scale up, and part of that is A, that computers have gotten better, but B, that we've managed to parallelize in such a way that we can speed up projects by running on either high performance computers or clusters, or even just a local computer that's got multiple cores. And in an ideal world, we'd want a case where if we were to increase the number of computational units we're using by a factor 10, then we would want the solution to our problem to come 10 times faster. So for instance, if we were to run on 10 cores versus 1 core, ideally we'd want the 10 cores system to run 10 times faster, or to be able to run a system that's 10 times as big. However, unfortunately, this is not the case, and very rarely the case. So now I'm going to switch to actually sharing my entire screen. Does that work? That's often rather unhappy when I try to do that. Yeah, that's just not happy when that. because I want to give a rather concrete example. Yeah, that works. Cool. I want to give a rather concrete example. So let me log into ARCHER2, and you're all welcome to log into ARCHER2 and do this with me if you want, because all of this material is available, and I'll show you where you can get it. It's login.archer2.ac.uk. I remembered my password, which always makes me way more happy than it should. Cool. So I'm moving to my work directory because now I'm going to run a couple of jobs. And specifically, I'm going to do I'm going to look at performance. And what I'm going to ask is the following question: how do we measure performance? And indeed, if while I'm going to quickly run this job, I'll show you what job I'm running. I'm going to run a quick LAMPS job because LAMPS is a nice little molecular dynamics code which is predominantly used in like for physics and physical chemistry problems. A bit less so. It's a bit less, well, definitely less efficient than GROMACS for any biochemistry and biological physics system, but it still has a number of really cool functionalities. The job I'm going to run is on the short queue using the reservation. So I've got all of the headers that we've been using yesterday. I'm using the module EPCC job env, which I mentioned yesterday, and I'm also loading LAMPS in order to get access to the LAMPS executable. Now, what is it? This bit of the code I'm gonna just brush over and not really talk about it too much just now. It's just here I'm just making sure that the different will run on the correct cores within a node. I've asked for a single node, and I'm going to run a number of jobs. I'm going to run a 64 core LAMPS job on a system which will have 20 by 20 by 20 for 4,000 total particles. And then I'm essentially going to run it on one core, 2 cores, 4 cores, 8 cores, 16 cores, 32 cores, and 64 cores. The idea being I want to see how this job, how quickly this job runs as I increase the total number of cores for it to run on. I'm going to submit the job. And then I'm going to, while it's running, it takes about 1 minute to run. I'm going to go to TA017 work/TA017/shared LAMPS performance. And you'll see that all of the, well, two things. One, the LAMPS input script that you need to run these jobs is in this shared directory, as is the submission script that I just ran, substrong. Is the submission strict here because we're looking at strong scaling. I'll explain what strong and weak scaling are in a sec as well, but yeah, this is exactly the same script that I ran. So if anyone wants to copy this and run the run this while I run it, I'm gonna put this in the chat. Apologies for the terrible tunnel. There we go. That's where you can all get it if anyone's following along. So by now, I would be very surprised if the job's not finished. I can check this by using SQ. Oh, it's still running. Jolly good. But I imagine that there's going to be a number of jobs that have finished. While that's going on, actually, I'm going to launch another set of jobs. No, I'm not actually. I'm going to stay here. This much must be finished by now. There we go. It's done. So now I've got a number of outputs. So not only do I have the Slurm output, which tells me all of the runs, it's going to be complete gobbledygook because I had a number of runs running at the same time. It's going to be pretty meaningless because every single run happening at the same time is going to output at the same time. I sort of did things to make this go faster. Actually, it doesn't look too bad, but we're not interested in this. We're not interested in slurm.out. What we're more interested in is the log files. So 01_.log is going to be the log file for the job that I ran on a single core. And I realize I should have named them _core rather than _proc. That's my bad. I can fix that later. And this is a LAMPS output file. I'm not going to talk too much about LAMPS because this isn't the purpose of the course. What I'm really interested in is the information at the bottom. So I ran for 10,000 time steps. I ran with, where is it? 4,000 atoms, 8,000 atoms. Sorry, for 20 times 20 times 20 is 8,000, not 4,000. Just to give you an idea of the job. And right at the bottom, it'll tell me the total wall time was 1 minute and 18 seconds. And actually, it gives me an even better breakdown. Where is it? There it is. The loop time was exactly 77 seconds on one processor. And if I look at the loop times for another processor count, let's say this one, I can look at the loop time. And you'll see that the loop time on 2 processors is 40 seconds, so faster. This is great. This is what we were saying. We want to be able to run on more cores in order to get faster outputs. Okay, so how much faster is this now? How do we quantify how much faster this is? So for the next steps, I am going to do 2 things. The first one is I am going to extract the information that I'm interested in. I want to extract loop time. And I want that from all of the log files. So there you can see all of the loop times. Starting with one processor, it takes roughly 78 seconds to run, and then it goes 41 seconds, 21 seconds, 11, 6, 3, 2. This is clearly looking like it's increasing. This is great. Running on more processors goes faster. But now the next question is it efficiently going faster? I.e., is it worth us using that many processors, or is it actually the case that we're getting to the point where it's not as efficient to run on 64 processors? Well, how do we check that? The easiest way to check that is let's look at a few plots. So I am just quickly gonna, I think it's take this output and make it into a slightly more legible format. And I think I always forget. I think the curly bracket should actually be there. Let me check. There we go. So what I've done here is, this is just a bash command. Again, not going to spend too long on this, which is taking this output here, and it's looking at the 6th column, which is this column that tells you the number of cores we were using, and the 4th column, which is the column that how long everything's been. And I'm gonna just put it in an output file. And if I look at output.out, it's just telling me number of cores, how long it took to run that same job. One of the cool modules that you can get on ARCHER2 is we've got GNU-plot. GNU-plot is a fantastic little program for plotting things. And let's plot our results. Plot output.out, use columns 1, 2, and with lines and points. There we go. And this is plotting, well, at the moment, it's not plotting anything particular. Well, it's plotting the wall time, so how long it took for the LAMP simulation to run as we increase the number of processors. So far, so good, but still, it's not telling us efficiency yet. So one thing that might be interesting to see is how fast is it in comparison to when we ran it on a single processor. So on a single processor, it took 77 seconds. So how much faster is it? What's the speed up for running on 2 processors versus 1 processor? And so what I'm plotting now is I'm plotting how much faster, i.e. how many times faster is it going as we increase the number of processors. This is the speed up. And the plot is in the background. There we go. And as you can see, I'm going to log scale this because that looks a bit better, actually. Hopefully you can see this. Let me know if it's a bit too small. I can actually change the line width and two. Yes, 2, I think. Is that right? There we go. That's a bit bigger. And as you can see, as we increase the number of processors, the time goes faster and faster. But is it going as fast? Is it 100% efficient? Well, I guess the easy way to find that out is let's compare it to a function f of x equals x, just a simple linear function, because ideally we're going at least linear, or we're going at a linear speed up. So whenever we double the number of processors or cores, we're hoping that the speed will double. So let's compare to ideal speed up. And there we can see quite clearly that for low processor counts, we get a decent speed up, very close to ideal. But as we increase the number of processors more and more and more, the speed up decreases. So we've talked about the idea of speed up. Another thing that's another value which might be of interest is what's the speed up compared to the number of processors. And what that will show you is essentially it'll show you what is the gap between our, sorry, give me one sec. I'll make that line bigger. What is the gap between the purple line and the green line? And we want that gap to be as small as possible. And one easy way to do that is to look at the efficiency, the serial efficiency of your system. And the way you can do that is by looking at the total time it takes multiplied by the total number of processors. And if you look at how long it takes on one processor divided by the total time it takes on more than one processors multiplied by the total number of processors, you get an idea of how much effective computational work has been done here, i.e. how long it took for the processors to carry out this job. And there you can see it starts at 1, and 1 is perfect. Essentially, 1 is the, what's the word I'm looking for? 1 is the ideal situation. However, as we increase and increase and increase the number of processors that we're using, that we get further and further and further from ideal. So why is that? Well, going back to the slides. So I've mentioned already how we measure parallel performance, but here it is in a simple line. It's telling you right here, the speed up is equal to the time it took on one processor, on one core, versus the time it took on a larger number of processors. That is the one of the plots that we looked at. And we also discussed the efficiency. And the efficiency is it's the speed up divided by the number of processors, and ideally it should be 1, but it's very rarely, it's very usually less than 1, and that is the second graph that we showed. So this is a measure of the efficiency. I've not really talked about or shown the how to find the serial efficiency, but here's the equation for it, and essentially the serial efficiency is you take your it's a measure of the best time that you got divided by the time for one processor. And the way that works is, actually, I'll explain the serial proficiency in a second because it'll be easier to describe. So what we've been looking at so far is strong scaling. And strong scaling is essentially one of the easy ways to talk about strong scaling is to talk about Amdahl's law. And the question, first of all, is that we're trying to answer is why is the efficiency getting less than 1, and why does the lack of efficiency increase as we increase the number of processors? I.e., why is this line not straight, or why is this purple line not on this green line, and why is it getting further and further away? And the best description for this is Amdahl's law. And Amdahl's law states quite simply that the performance improvement to be gained by parallelization is limited by the proportion of the code which is serial. What does that mean? Well, most codes will have parts of them which are which can be run in parallel, i.e. they can be split across multiple processors to make them go faster. But there's always parts of a code that must be run in serial, that can only be done by a single core. And those are the bottlenecks when you're trying to parallelize your systems, at least according to Amdahl's law. The easy picture for doing this is if we look at this picture right here, where we've got in black, the block is the serial part of the program, and that must be run on one single processor, no matter how many processors you throw at the program. And then the white bit here is the parallel part of the program, and that can be reduced by running on more processors. And as you can see, as we run on more processors, the white part will decrease. The parallel part will decrease in the amount of time it's taking, but the serial part, the blocks at the top, will stay the same, meaning that the proportion of time taken that the program takes that is in serial versus in parallel increases, and the speed up gets less and less and less. And this is what the number of processors in speed up shows, of the speed up gets less and less and less. And this is why we have this divergence that we see here. Now, so far, this might seem all very abstract, so I'm going to try to explain this with a slightly more simple problem, or more easy to visualize problem. Arno, Holly, and I are based in Edinburgh, so let's consider that Arno, Holly, and I wanted, for whatever reason, to go suddenly to the Empire State Building, and let's pretend that we could as well. Let's consider a trip from Holyrood in Edinburgh to the Empire State Building in New York. The distance from Edinburgh to New York is roughly 5,000 kilometers, and we're quite lucky in this fake world that I've invented, insofar as we can either travel by jumbo jet, which has a flight speed of 700 kilometers per hour, or a Concorde, which has a flight speed of 21,000 kilometers per hour. Now, given these numbers, how would it take us to go from Edinburgh from Holyrood to the Empire State Building? Please do feel free to write your answers in the comments if anyone has any ideas. Or in here. So how fast would it be? Anyone want to venture a guess? No guesses? Maybe I've lost everyone already, or my sound is off, I'm not sure. Right, well, in that case, let's just jump straight into the solution. Now, you might be tempted to think that because we're flying 5,200 kilometers, you might be tempted to think that with the jumbo jet going at 700 kilometers per hour, that would take around 7.5 hours to do. And then the Concorde, which flies at 210 miles per hour, would take, that shouldn't be 2 hours, that should be a bit more than 2 hours. It should probably be 2 hours and 40 minutes. Let's call it 2 hours and 40 minutes, that's a typo, I'll fix that. So you might think that the total speed up is roughly 3 times faster. It's 3 times faster to travel by Concorde than it is to travel by jumbo jet. However, in this problem, we're not starting in a plane that's about to take off, and we're not aiming to just land in New York, or indeed in New Jersey, maybe. What we're wanting to do is we're specifically wanting to go from Holyrood to the Empire State Building. So there's extra costs to this. There's the trip to Edinburgh Airport, which takes roughly 30 minutes. There's security and boarding, which is probably an hour and a half. Plus, you know, I'm sure that Arno would need a coffee at some point, so that'll be included in the hour and a half. There's US Immigrations and Customs, another hour at least. And then there's the taxi ride from the airport to downtown New York, so we can make it to the Empire State Building. So there's an overhead. There's an overhead of roughly 4 hours that can't be reduced. And regardless of whether we fly by jumbo jet or Concorde or even some fancy military grade aircraft that can go even faster than Concorde, which definitely exists, it doesn't matter because this overhead still exists, which means that the speed up is much closer to about 1.9 than it is to 3 to 3.7. because the total trip time it goes from because the total trip time isn't reduced by as much. And in this case here, what's the word I'm looking for? The planes, the taking the Concorde as opposed to taking the jumbo jet represents the parallelizable part of your code, whereas the trip from the airports and customs and all of that represents the serial part of the code. So Amdahl's law suggests that the shorter the journey time, i.e. the shorter the distance we're trying to go, the more important the serial overhead is. And to give you an idea, if we were wanting to fly instead to Paris, it would take 1 hour by jumbo jet and probably 20 minutes by Concorde. This fixed overhead still exists, which means that the saving of 40 minutes by taking a Concorde is not as impressive because the total journey time is still 4 hours and 40 minutes as opposed to 5 hours when you take everything into account. I've written a proof of Amdahl's law here, but we're not going to go over this. If you're interested in this, you can have a look at it yourself at a later point. Now moving on swiftly to Gustafsson's law. And Gustafsson's law is a twist on Amdahl's law. And Gustafsson states that, yes, it's entirely correct that if you were to just increase the number of processors for a fixed-sized system, then eventually you'd get to a regime where it's not worth parallelizing anymore because it's a misuse of your resource and your performance is dominated by the serial part of your program. But Gustafsson's proposal is simply that's not what we should be thinking about. Instead, what we should do is we should run larger jobs on a larger number of processors, on a larger number of cores. Because if we run larger jobs, then the parallelizable region will increase. And therefore, we're still limited by the serial part of the code, but this becomes less important because there's more stuff to parallelize, more stuff to make go faster. And I've got here, again, just to quickly show, a similar code here, which I'll run in the background while we do our analogy, where I'm running exactly the same lamp systems, but instead of all of them being 8,000 atoms large, I've got on one processor, I'm running an 8,000 atom large system. On two processors, it's a 16,000 atoms, then 32,000 atoms, etc., 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 etc. So as I double the number of processors, I'm doubling the number of the size of my system. I'm going to run this quickly. And now, hopefully, according to Gustafsson's law, the idea will be that as my system size doubles, because I'm using twice the number of cores, hopefully, I will be all of the jobs should take the same number of time. So because the system on 64 cores is 64 times bigger than the system on 1 core, hopefully they should take roughly the same amount of time. And this is weak scaling. The previous idea of you can increase the number of cores and look at the speed up for the same size job, that's strong scaling. So this is what we mean by strong scaling versus weak scaling. I'll show you the results to the lamps job when they finish, but before we do that, I wanted to ask another quick question, and hopefully I'll get more answers this time. But let's consider the same trip from Holyrood, or a similar trip from Holyrood, Edinburgh, to the Sydney Opera House in Australia. Now, the distance from Edinburgh to Sydney is much larger than the distance from Edinburgh to New York. It's roughly 3 times larger at around 17,000 kilometers. As before, we've still got our jumbo jet and our Concorde, which is just waiting for us to go on there. Let's assume that customs times, moving to the airport times, etc., takes the same amount of time. What's the speed up in this case? Does anyone want to hazard a guess as to what the speed up is? Bearing in mind you can calculate the speed up with the equation with this equation here. So, and in this case, n equal the time for on one processor is the time on the Jumbo Jet, and then the time on more than one processor is the time on the Concorde. I noticed that there have been no guesses hazarded, which is rather sad. But this one is not a trick question, unlike the last one. This one is quite simply, the Jumbo Jet will take about 24 hours to get there, which makes a total trip of 28 hours when you include the 4 hours of customs, immigrations, travel, etc., whereas the Concorde will only take 8 hours, much faster. It's 3 times faster, right? Which makes the total trip time 12 hours, which means that the speed up, the amount faster that you're going, is 2.3 times faster as opposed to 1.9 times faster for the trip to New York. So this is showing you Gustafsson's law in effect. The bigger problem, i.e. traveling a further distance, means that using more processors, i.e. a faster plane, will have more of an effect. Oh, sorry, Pedro. I should have waited a bit longer. And that is Gustafsson's law. So hopefully my jobs will have finished. It looks like they have. And it looks like they've all run in some amount of time. Now, when I ran this before, there was an issue with one processor, but it seems to have run fine. That's perfect. So I'm using the same command to output the loop time to here. And as you can see, well, 2 things to note. The first one is the loop times now are much closer together than they were before, which is a good sign. The second thing to note, however, is the loop times do still increase. And if we were to that should be about right. That is totally not right. Sorry, one moment. There we go, that's why. If we were to look at the speed up, or the rough speed up, output, it's 87 seconds rather than 77 seconds this time. Must have just gotten a slightly slower node. That can happen. There we go. If we look at our performance, well, our speed up. Our speed up, we expect it to be at around 1, and it starts off being near 1, and then it quickly drops to 90%, and then even to around 85%. So even though we're using a bigger amount of job, we are still not at perfect speed up, but we're still getting by increasing our system size, we're still getting less of a drop-off than we were before. And that's the idea of Gustafsson's law, the idea of if you want to use more processors, maybe you should consider running larger jobs. The final quick thing I want to mention, there is also here a proof of Gustafsson's law, which I'm not going to go over, but you're more than welcome to read it if you're interested. And the final thing I wanted to mention is load imbalance. And I realize I'm going a bit over time, but I shouldn't take more than 2-3 minutes on this. Load imbalance is, so far, we've been considering a case where all of our cores are equally busy when we run parallel jobs. And Gustafsson's law and Amdahl's law only really apply to the cases where all cores are equally busy, doing the same amount of work all of the time. However, what happens if some run out of work while others are still busy? This is load imbalance. And so for this, a last quick analogy, let's consider that you have 4 people who are tasked with filling boxes with cans. Each one of them is in charge of one specific type of can. So Anna, for instance, is in charge of the chopped tomatoes, and David is in charge of the sweet corn. And each box needs a certain number of different cans. So Anna needs to put 6 chopped tomatoes in the box. Paul needs to put 1 can of chickpeas, David needs to put 3 sweet corn, and Helen needs to put 2 cans of spinach in each box. And it takes all of them 1 minute to go to the shelf, grab a can, put it in the box, and because it's imaginary land, they cannot carry more than 1 can. Let's imagine they're really big. Now, how long would it take to finish this entire job? Please feel free to put your answers in the chat. I'll give it a sec. But so all of them can put cans in the box at the same time. They're essentially our processors. It's just that some of them have to put more cans than others. So how long does it take to finish this job? 6 minutes is exactly right. Because each task takes 1 minute, it'll take 6 minutes to be fully complete. And the entire job is based on how fast Anna, who's doing the most tasks, does her tasks. And because the jobs aren't evenly distributed, it means that we're unable to do this faster. So scalability isn't everything. It's also important to think about making the best use of all of the processors that you're using, not just some of them. So how can we quantify this load imbalance? One way to do it is to think of a load imbalance factor, which tells you, which is the ratio of the maximum load versus the average load. So for this job, for this job here, the maximum load is Anna. Anna has 6 tasks to do, so the maximum load for this is 6. The average load is the total number of processes, so 12, divided by the total number of cores, so 4. Our average load should be 3. So our load imbalance factor is going to be equal to 2. 6 divided by 3 is 2. This means that we could potentially reduce the processing time by a factor of 2. We could reduce the speed at which they packed that box by a factor of 2 if we were a bit more clever about the way we distributed the tasks. So with that, I'm already 5 minutes ahead of further than I should have done. I'll quickly point out the key points, which are, as the number of cores are increased, performance rarely scales linearly. And it's something worth considering when you're running on really large number of cores. Make sure that you're getting the most out of your processors and your cores. Scalability changes as the size and complexity of the system is changed. If you run a bigger system on more cores, that's usually better. And finally, scalability is completely meaningless and is not the thing you should be worrying about if you've not distributed things evenly amongst your processors. It is both. One of the questions is load imbalance in GROMACS. Is that between distribution of tasks in GPUs and cores, or just cores? It can be both. At any time that you've got something, part of the resources that you've asked for that's sitting idle, that's a waste of that resource. And because usually on supercomputers you are paying for access to those resources, that's also a waste of money. And it's also a waste of, so it's important to try to make sure that everything is running, is doing something, because if it's not, you're paying for something that's sitting around doing nothing. And with that, I will finish this section. I believe that the next part is the second part of the hammer practical. So I will hand over to Arno. I hope that made sense, and if you have any questions, please feel free to ask them in chat. I'm more than happy to answer them even during the hammer practical in chat. But I realize that was a lot to take on and take in not very much time.
Okay, thanks. So so now's a chance to spend some more time working on the hammer practical, and I'll do a wrap up starting at no sooner than 10 minutes past the coming hour. So yeah. So while people are working, and I can see Julian having a look at the instructions, and it reminded me actually of something that's we can actually talk about now rather than waiting until the outcomes, because it's just an aside, but it's about this consider this part, which is talking about running using srun to launch multiple instances of phammer in parallel. So I was wondering, does anybody have any idea what will happen, or if you tried it, have you seen what happens? So maybe nobody has tried it, or everybody has gone off to grab a coffee, which is also perfectly acceptable. I can also discuss this the outcomes. Maybe some people are away right now and might be back at 10 past. Yeah, so if nobody responds, I'll probably just leave it until the discussion at 10 past, when I know that people definitely are there. That's fine.
Hey everyone, there's a couple of you saying that you're getting a reservation error. That's absolutely, that makes sense. The reservation we were using yesterday ran out at the end of the course yesterday. You should instead be using the reservation number TA017_139 instead of 138, and I'll put this in the chat. That's the new reservation number. If that one doesn't work, let me know, because then there isn't.
Hi Tammy, yeah, that'll be because the no ally option should be an option that is put after the phammer command rather than directly after srun. Okay, so yeah, as I said, Tammy, I mean it's oh sorry, Tal, I misread Tal. That's the thing you should be doing, putting no ally after phammer rather than srun. Anyway, I know some people might still be working on getting results for the MPI parallel case, and as I said, you can do this later as well. I'd encourage you to work through it. But I thought I'd take the chance now before the break to have a wee discussion about wrapping up the what we take home essentially from this exercise, and see what you find. And I'm going to try to summarize, and we can think about this, think about what you're encountering, or what you probably found in light of what Julian talked about with regards to speed up, how fast things go, and the sort of the efficiency of that. Okay, so the document that is showing is in the, you can access it up with a link here. It's in the part 2 practical course materials. I'll just grab the link, because I'll be going back and forth between the slides, so you may want to look at it yourself stationary, so you can okay, so what you may have found is something like the following. So here you can see the first data set that we were querying against, the mammals data set, so the smaller one of the two. And what I've plotted here is the elapsed wall time for both the pthreads case using the CPU option. I say pthreads, we haven't talked about what pthreads are versus threads in general, but it's not so important. Point is that this is multi-threading, so it can never span more than one node. And also the results for the MPI parallel case. So what you see here is a little kind of similar. What you may have noticed, well, no, let me ask actually, did anyone notice any relationship between the wall times, especially for just 1 core, 2 core, 3 core, if you did that, or maybe 4 core, just the small numbers of cores? If you happened to have run the same queries with both the CPU version and the MPI parallel version, did you notice a relationship between the values being very similar? And I mean very, very similar. So maybe not. So if we were to look at this carefully, what you might notice is that, so we know that we cannot run the MPI parallel case on 1 core. That's simply not been implemented by the developers. They, in principle, they could make it work, but it's not been implemented. So what you would find, however, is that the result on 2 cores for the MPI parallel case is actually very, very close to the result on a single core for the pthreads case, for the CPU case. So and the same goes for 3 cores and 2 cores. So the it's especially clear that for small numbers of cores that the wall time, elapsed time for the pthreads case is always the same as the MPI case running on one more core. Now, why is that? It's because, so the way that they've actually parallelized, the way that the developers have parallelized the problem of doing the sequence alignment is they've taken this kind of task farm or model that I outlined yesterday, where there's one process or one thread that's responsible for coordinating the assignment of what other processes or threads, i.e. what other cores do, the work they do, and the other cores are all actually doing the work. However, there is, in the case of the CPU version, there is in the one core case, so it essentially launches both a coordinating thread and also, which is kind of seen as a helper thread, and an actual worker thread. Whereas for the MPI case, that doesn't happen until it runs on two cores. So that's the basic reason for the similarity. But this subtlety aside, which is something peculiar to pHammer, what we're seeing is, clearly the wall time gets gets better, speeds up. The question is then, how much does it speed up? So if we continue then looking at the, if we plot the speed up for both runs compared to ideal, then we can see that, okay, it looks not that great, because we can see that at around, so the MPI case looks a little bit better. So around, so that would be the 32 core mark. The MPI case is still closer to the ideal performance than the CPU multi-threaded case. It's worth pointing out here that in each cases when we're computing the so this is worth pointing out. As I said in the instructions, when you're computing the speed up for the MPI case, it's relative to the smallest numbers of cores that you can run on, which in this case is 2. That's why I mentioned that you should divide by to get the speed up, you should divide by the runtime on 2 cores, because there's no, you can't run it on 1 core, so you kind of are forced to do that. Then the question is that representative somehow? Well, yes, in a way, because then we know that in the MPI case on 2 cores, there is still kind of one core that's actually doing the real the work. We're not trying to characterize anything, fundamental kind of. We're just using this efficiency characterization as a way to find a sweet spot for how many cores we should use. What's worthwhile pointing out here is that so we've computed these speedups for the MPI parallel and the CPU parallel case, in each case by relative to their performance on the smallest case we can run. So when you're looking at so MPI being better here for a given number of cores, you have to watch out what that means. It doesn't mean that it's faster, because as we saw above, they're very similar. It just means that relative to its slowest performance, it speeds up. It seems to have a better speed up running on more cores. But this case's data set is clearly limited. It doesn't scale very well. So the strong scaling, for fixed data set size and increasing number of cores isn't great. So then we look at, well, can we run? Okay, so the science you're doing determines what data set you're using. But let's just see as a way to understand how the parallel performance, what happens when we look at a larger data set. So that's why I suggested looking at the Swissprot, Uniprot all, not just mammals. And there, if you plot the speed up there, and here we're doing it just for the MPI case, because we know they're kind of similar, and but MPI will simply get us across to more cores. It'll allow us to span beyond one node. We can see, okay, it is better, because here we're going, so we're going up to 256 cores. So it is better. It does drop off, but it does allow us, it does scale better, and for a given number of cores, it scales better than the smaller data set. So we're observing this phenomenon here of it's not a mystery. I mean, if you give a piece of software more work to do, then each task then you are able to use more cores more efficiently because there's simply more work in total to do. Now let's think about this sweet spot of efficiency. So if we compute the efficiency, which is the parallel efficiency, which is how far for a given number of cores, how far is it from being true that the running on p cores goes p times as fast, where 100% parallel efficiency, or a factor is 1.0 in this case, would mean it is actually p times faster. Now, you may ask what's going on so this is the results for the dataset for the MPI parallel case. And you might ask why is the efficiency increasing, first of all, and that's because of this, that's just a reflection of the fact that actually we cannot run on one core. So, but really, if you regardless of whether you kind of extrapolate to one core or if you base it on two cores, that moves around the peak of the efficiency only a little bit. But the point is that you can see the peak of the efficiency is below 50 cores, and then it drops down to, once we get to a single node, which is 128 cores, it drops down to even just below 70% parallel efficiency. So how many cores should you run on? Well, you can go faster if you use two nodes, but not very much faster. And the parallel efficiency really isn't great. It's around 40% or even a bit lower than 40%. So this problem really doesn't scale out very well. So we might have anticipated, okay, this thing sounds as if sequence alignment sounds like it's the kind of problem which might be easy to parallelize because you're just comparing sequences to the whole database. But turns out there are limitations. And in fact, if you look at the documentation at the manual for Hammer, the Hammer suite, they mention, yeah, Hammer, it's okay, it does parallelize, but it doesn't necessarily scale amazingly. Just out of interest, if we compare these results to the results from the predecessor to ARCHER2, namely ARCHER1, we can see that same plot of the parallel efficiency of the MPI parallel case. Actually, it looks like when we go out to let's compare the equivalent about 128 cores, it's still a bit higher. It's just under 80%. So what's going on? Has the software gotten less efficient, or is ARCHER2 somehow less efficient? Well, no, because let's step back a bit. So we can see here that, and again, this is reflected in, if we look at the speed up, it looks kind of better than on ARCHER2 than the results we showed above. But if we look at the absolute runtimes, actually, on a single core, on a core-for-core basis, the runtime has decreased a lot. The vertical scale for the elapsed time here is about 200. For the ARCHER2 result, it was 80. So the amount of work is not just a static thing about the code and the problem you're trying to solve. It's also about how the software algorithm works, which may have been updated to become more efficient since these results were obtained, but also obviously the hardware you're running on. So the cost is a function of the problem, but also a function of the hardware you're running on. So if the ARCHER2 cores are more powerful, or the software is newer, which means that even on a single core, it's already faster than these older results, that means that there is essentially less work there to split up. So there's no surprise that even if all else being equal, the communications being equally, the communication overheads being the same, etc., there would you might expect that the parallel efficiency is worse, but it's fine because we're still getting faster results on ARCHER2, so that's great. So that's kind of how to think about these things. I have overrun a bit. I'm happy to answer any questions by chat, but I suggest that we do put time now. I'll answer them via chat so that people can go away and still see responses, and I'll address anything by speaking later on if useful. So we'll start again with the next talk, which is at, it's a kind of a practical, no.
Nope, the next one is yes. Computational building blocks.
Okay, at 22, the hour.
Right, everyone. I think we're scheduled to restart now. Could I ask everyone who is here to please put your hands up to show that you're here, please? Okay, perfect. Thank you very much, everyone. We're definitely core 8, so I will start the lecture now. And give me 1 sec to share my screen. Right, that's right. Right. So between now and the lunch break, we wanted to talk a bit about computational building blocks, and we wanted to sort of explain to everyone what makes up a computer, what makes up a supercomputer, what are the similarities between the two, and essentially starting from scratch, what are the Lego pieces with which you build up a computer, and I'm going to talk about the software side of things, talking about the operating systems, processes, and threads, and finally explain to you, what we mean by threads and why you cannot use threads across multiple nodes on ARCHER2, that sort of thing. And after which, Arno will talk about the hardware side of things, where he'll discuss the difference between a node, a core, a node, a processor, a core, etc., etc., etc. Hopefully that'll help elucidate some of the language that we've been using so far. So for this, I'll be both doing the presentation and showing you bits of how it works on my own work laptop, just to emphasize the points where necessary. Right, so here we go. In this lecture, I will be talking about operating systems, defining what an OS does, what is meant by an operating system, what operating systems are used on high-performance computers. I'll also be talking about processes, how they're managed, what they are, and threads, and how they work on accelerators. So starting with operating systems. What are operating systems? Well, I'm pretty sure all of you know what an operating system is already. So probably better than to ask what an operating system is. A better question would be, do you know what operating systems you are using at the moment? And if so, could you write which operating system you're using? So we've got one Windows, Linux, Windows, Macs. Yeah. Yeah, those are the big three. Yeah, so we've got the big. There's a lot less Windows users than I would have anticipated, which is interesting. But yeah, that's right. So Windows is actually the operating system that's most used throughout the world. The primary competitor to that is probably Mac OS, and then you've got certain people who do use Linux. Personally, I'm on Linux. I'm using I'm running Ubuntu on my my local laptop at the moment. So so we all know what an operating system is, and we can all name what our operating system is, but what do they do? Well, the operating system is the underlying software that steers a computer's operation. It will run all of the processes that are needed. It'll create a nice graphical user interface that can be used. So everything that you can see here, the fact that you're able to see me share my screen with you at the moment, that's all run by my operating system, or at least all set up by my operating system that's making sure that all of the various bits of program that allow this to be done are able to do this. But it does a large number of other things. It'll manage how the system's resources are used. So it'll manage, say, how much of each processor is used at any given time. It'll manage where the memory is distributed. You can manage disk space through it, network connections, all things like that. And also it has a number of other utilities for anyone who's wanting to program to help make it easier to program for certain hardware. So when I say it manages things, part of the reason I'm doing this locally is because I've got HTOP installed. And here you can see every single process that is currently running, every single tiny task that is currently running on my laptop is in this list here. And there are a number of them, and this is a nice little tool which tells you what CPU power is it using, how much of the memory is it using, and then at the top it tells you in a nice graphical fashion, well, how much of the total of each processor is being used, how much of the memory is being used, none of the swap is being used, which is good, and things like that. All of this is being handled by my operating system. So an operating system, as you've just seen, it allows multiple programs to be run concurrently on hardware. Some operating systems, most operating systems now can even allow multiple users to access the system and run applications at the same time. So able to switch users in a lot of operating systems, modern operating systems, so that you have a session going while someone else has a session going, and provided you're both able to access the machine, you should be able to do that. But the other thing as well is it controls all of the processes and threads, which we'll talk about more a bit more. But processes we've already alluded to. It keeps track of each and every single one of these processes, including, most of them are me, most of them are Firefox, but some of them are run by root, for instance. So if I were to do this by user rather than anything else, you see that it's managing a number of processes by a number of users. This is all being done currently by my OS. Now, on HPC systems, traditionally, they used to always use Unix, and different vendors would have their own version of Unix. So you used to have the Sun version of Unix, you used to have the Cray version of Unix. However, recently, there's been a shift towards using mainly Linux systems. Some HPC vendors will have a modified version of Linux, which, in order to be able to sell it. So on ARCHER2, for instance, Cray have made their own version of SUSE. And they'll also, part of the reason for them doing that is to really have an operating system which is specifically trimmed and geared towards high-performance computer. And that line should have been updated, but at least as of November 2017, all machines in the top 500, so all of the top 500 most powerful supercomputers by petaflops, were Linux machines. I don't know if that's still the case. I would be very surprised if it isn't. And apparently it might be, depending on how IBM does, because apparently only IBM still uses Unix. The important thing to note is Windows and or Mac aren't the ones that are really used for HPC systems. So on the compute nodes, on ARCHER2, the compute nodes will have a slightly different operating system than the login nodes. The reason for this is, going back to this picture, if I go down, I need to, that way, don't I? Okay. Oh, there we go, that was faster. If I go down all the way to what root and the system is running, there are a number of processes that are run by root. As you can see here, there's a number of processes that are run by root. This is mainly the OS, but also a number of systems, system logs that are being written. All of these root processes are the OS running them, and some of them are quite useful for me. So for instance, this one, GDM, is the graphical user interface. It's what allows me to have a screen rather than a command line for you to show you everything. And all of this is being run by root. Now, obviously, compute nodes, you don't need a graphical user interface on a compute node, because users should never be running graphics things on a compute node anyways. A lot of HPC vendors will trim down their versions of the operating systems in order to make compute nodes be more efficient and better optimized to run to run programs, so that more of the compute node's time can be spent running your job rather than running background tasks that the OS needs to use. And this is kind of what it's saying. Ways that the OS is optimized, well, it removes features that are not needed, like the graphical user interface or USB support. You're not going to go plug in a USB into a compute node, or I hope you won't. Reducing OS processes running in the background, that's what I described. Restrict scheduling flexibility. We'll talk a bit more about that in a sec. Binding processes and threads to specific cores, also we'll talk about a bit more in a moment. And then you probably already know this, having logged into Archer a couple of times. Usually for high-performance computers, you access the computer via a remote login, often using Secure Shell or SSH, and you'll have to transfer files over Secure Shell either using the Secure Shell copy (SCP) or the file transfer protocol. There's also another couple of ways that you can transfer files. And then the other thing, and it's something that someone pointed out towards the end of the performance lecture. For most systems, when you log into them, if you just SSH into them without using the -x command, so if you run something other than SSH -x or SSH -xy, you will not be able to run any graphical programs. You won't be able to use things like GNU plot or VMD or anything like that on the login node, because Xserver, the visual part of programs, will not be able to be transferred through SSH if you don't have that. Now, some of you will have noticed that when I logged in, I always log in using SSH and not -x, but I was still able to get GNU plot to work. For this is that I've, in my local system, added a quick alias in my bashrc file. Let me see. So I've made it so that whenever I type SSH, the program reads it as SSH -x, or just to make it easier. But yeah, so Xserver is disabled unless you enable it, and it is disabled on all the compute nodes anyways. And then the final thing about the HPC OS environment is that it is definitely meant for multiple users. If I SSH TA017, that looks about right. Cool. I think if this is the command, if I type users, it shows me from memory. So if you type the command users, it tells you all of the usernames of everyone who is currently logged into Archer2, or at least to login node 1 on Archer2. So I can see everyone who's currently logged in and who has a session open. Quite obviously, there's more than just me logged in, and indeed, probably some of you are still logged in at the moment. So always allows multi-user, because otherwise it's not much use being a high-performance computer. Each user is provided a home directory. We've kind of talked about this before. Quite often you can create anything and destroy anything in that directory. So I'm in my home directory. I'm going to make a directory test. I can make a directory. I can remove a directory. But if I'm not in my home directory, or a directory within my home directory, I'm not able to change anything. So if I were to try, I don't know, remove directory Arno, let's say, it tells me operation not permitted. I am not allowed to delete Arno's home directory because I don't have the correct permissions. Cool. And then users have limited permissions to change things. I've kind of already shown that. You shouldn't be able to have, or you should not have sudo access. And indeed, if you try to run sudo commands on Archer2, the systems team will be notified. They will then notify the support team, who will be in touch to ask, what were you trying to do? And if you don't answer appropriately, we do sometimes stop you accessing your account until you give us a good reason for why you used sudo, or explanation, not even reason. It could be I accidentally typed it because I was following some instructions online, but we just still need to know why you did it by accident. The software provided varies from system to system. What's there when you start varies from systems to system. And we can also add certain bits of it. When we first got ARCHER2, there were a certain number of software packages that weren't on that people felt were needed. One particularly popular one was Emacs. Emacs was not available when ARCHER2 was first there. Neither was Nano, and then our systems team installed it so that everyone could use it. There's also the module files and module system, which we've already talked about a bit, so I'm not going to go over that again. But yeah, so we obtained Emacs through the Linux package managers, but it's our systems team that needs to do this. No users can do this, and indeed the support team couldn't do this either. So in that sense, it's very different from, say, your local PC or your local Windows machine or Linux machine or Mac machine, because for all of those, you should have all of the permissions necessary to be able to run these commands and install whatever software you need. The command line you should know about, because that's one of the mandatory requirements for the course, but be aware that most HPC systems, when you log into them, you end up in, same as here, you end up with just a command line. And if you do not know basic shell commands, you won't be able to do very much. This is not the case for anyone on this course because, now quite a lot of systems will often offer a variety of shells. We've been using mainly bash, and by default you've got the bash shell. But if you look at, oh, that's not what I wanted to do. I wanted to run ls. If you look at that, so this is just listing the list of shells available on ARCHER2. It's got a couple of other outputs as well because I wasn't particularly careful about it. But there's bash, there's C shell, there's K shell, LK shell, MK shell, TC shell. We don't have Z shell, though that's quite a popular option for other people. You'd need to install your own if you wanted that. That's doable. And then often there will be basic operations in terminal. So there's going to be a text editor that's always available. I've already mentioned that we've got Vim. There's Emacs. I cannot use Emacs to save my life, but it's there. And then there's Nano, for those of you who use Nano. And so that's the operating system, the basics of an operating system on a high-performance computer, and roughly what it does, or what it provides. And we've talked about what it provides to a user-facing side of things a lot at the moment. Now let's talk about what it does in the background. And one of the really important things that an OS does is takes care of and runs processes. What is a process? Well, every single application is a separate process. So at the moment I'm sharing my screen, you can see that at least on this part of the screen, I've got Google Chrome open with these slides. Apparently I've got Firefox here. I've got my shell open here, my terminal open here, and then I've got an output file, which shouldn't be open, so let's close that. But I had an output file open there. For every single one of these visual programs, there is a process running. But also, as I've shown already, and actually I'm just going to run it on Arch. It's a bit, HTOP is a bit more graphical, but it's not available on ARCHER2. You can run top to see all of the processes that are running, and indeed who's running them. There's tons of them. The other one you can do is PSAUX will show you every single process that's running at the moment. And if we do WC-L, that'll tell us the number of lines. There's currently on login node 1, 3,870 processes running, quote unquote, simultaneously. Oops, wrong window. And every single application that's run is a process. And indeed, there will be, when I output this, a process for the PSAUX pipelined into WC-L, that'll be in there somewhere. And every single one of these processes needs to be scheduled by the OS. What do we mean by scheduled by the OS? Well, most modern systems have multiple cores. Each processor has multiple cores. The ARCHER2 login nodes have, I believe, 256 cores, as opposed to 128 on the compute nodes, meaning that up to 256 processes can run at the same time. A core cannot really deal with two processes running at the same time on it. So how does the OS make sure that, I've already mentioned there's a number of users on ARCHER2. How does the OS make sure that my job's able to finish quite quickly, but also any job that you do on ARCHER2 is also able to finish quite quickly, as well as any of the root systems? Well, what the OS does is it schedules the processes. It'll make sure that each process has an allotted amount of time in which to run, and it will suddenly want to start another one, and then pause that one to restart another one, etc., 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 looping in a clever fashion, which I'm not going to get into because I don't know how it works, frankly, in order to make sure that all processes feel like they're going quickly. This rapid process switching gives the illusion that applications are running at the same time. However, that's not the case. So the scheduling, what I've just described, these processes, the swap and interruptions in which processes are running happen at super quick intervals of roughly, there's going to be 100 swaps and interrupts every second. That's ridiculously fast. But that allows for everyone to feel like their jobs are performing adequately quickly. So on I've already mentioned that on a multi-core processor, the OS will schedule that number of processors at once. So my laptop is a quad-core processor with multi-threading, but let's focus first on the quad-core. It has 4 cores, which means that my OS is able to schedule 4 processes at once, more or less. ARCHER2, I've already said, the login nodes have 256 cores. That means that the OS can and needs to keep track of scheduling up to 256 jobs at any given time, interrupting them 100 times every second to allow other ones to run. It's a lot of work. And it's pretty impressive when you just take a second to think about this. Now, some hardware supports multiple processes per node. As you can probably guess, especially in older PCs, it's a huge limitation to only be able to run one single process per core. And a while back, I believe Intel are the people who developed it under the name hyperthreading, but I'm sure someone will tell me if I'm wrong in the chat. They found a method of making every single physical core, every single, in the case of my laptop, every single quarter of my processor act as if it was 2 separate logical cores, meaning 2 separate places where the OS could send jobs to. And all of a sudden, as far as my OS is concerned, instead of having a quad-core processor, I've got an 8-core processor, which means it can suddenly run 8 jobs in parallel, as opposed to just 8 processes in parallel, as opposed to 4 processes in parallel, which makes everything run faster and makes everything run a bit more smoothly, etc., etc., etc. For those of you who are wondering, all ARCHER2 nodes have multi-threading. There's 2 things. The first one is that potentially on the ARCHER2 compute nodes, you can launch jobs on up to 256 cores because there is that number of logical cores. This may or may not affect your job completion speeds. And indeed, we'll do a couple of practicals to demonstrate this in the GROMATS tutorials. But the other thing is in the login nodes, that means that there's 512 effective processes on which these effective cores on which these processes can be run, which is enormous. So this is known as symmetric multi-threading, or SMT, and we'll refer to it a couple of times later. So that's processes. The next thing to talk about is threads. And threads are essentially sub-jobs in a process. So let's say you've got a super large process, and but it's able to do, like, there's 4 parts which are able to be done at the same time. Well, you could write the program such that that one process will use 4 threads. And it's kind of like a child or branch process for the main parent process. Each thread, each process must have at least a single thread, because each process is a single thread, but some processes can have multiple threads. The threads in the process have access to the shared memory, i.e. the memory of the parent process. What does that mean? That means that if I'm running a large process that requires 4 cores, the OS will allocate the memory needed for to run 4 cores. And actually, the way it usually works is that your total memory will be divided amongst the total number of cores you have, and then the OS will say, well, this process is running on 4 cores, so you should get I don't know, let's say you have 16 cores total, you should get 1/4 of the total memory. There's ways to play around with that, but very hand-wavily, that's what's happening. And so if you're running a process that uses 4 cores and has 4 threads in it, i.e. 4 child processes, the memory allocated for those 4 cores is shared between the threads, which means that anything done by any one of those threads can be seen by any other one of those threads, which can save a lot of time which can save a lot of processing time. You know, instead of having to compute this value again, having to read this value from wherever it's stored, I can just see whether my brother thread has already, or sister thread has already finished this, and read that input from it. So OS scheduling is aware of threads and takes care of this. I guess, yeah, so a nice way of describing threads, rather than making it nebulous and hand-wavy like I've just done, is to think of a computer game. You're playing a computer game, and in terms of thread, there'll be a different thread for, you know, controls for the spaceship. So when I'm moving the spaceship, there will be one thread sort of following which direction I'm moving in. And then there will be another thread to follow which way the missile that's about to hit my spaceship is going. And there'll be another thread for keeping track of where the spaceship is and reading and understanding the keyboard inputs that I'm doing. But because they are threads of the same process, they all share the same game memory, e.g. the screen. So threads with multi-core processors. Multiple threads can operate at the same time on the same data to speed up applications, but it cannot be scaled beyond the number of cores managed by the operating system. So you can't have more threads than a single operating system is able to run. And here we get to the answer from one of the questions yesterday, which was, why can't I share memory between multiple nodes on ARCHER2? And the answer to that is, each individual compute node has its own individual operating system, which means that they are not able to share memory for threads that are run across multiple nodes. Now, there are some HPC systems that are starting to look at this shared memory distribution so that you're able to do that, but ARCHER2 is not one of those. So we've kind of already talked about memory and how it's done. And why would you bother using threads? Well, it's an effective speed up. Essentially, if you're able to split your parent process into 2 equally sized children threads, you can potentially get your system to run twice as fast. It's the same reason as why we parallelize code. Finally, a quick word on accelerators. GPUs and general purpose GPUs provide a lot of computational power for low energy consumption. I mentioned yesterday already that essentially GPUs are processors with a super large number of very weak cores. All of those weak cores are able to share the same memory, and often GPUs will have a large amount of memory, much larger than, is it much larger than? I think it is much larger than an individual core, but can check that, or an individual CPU processor. And so what does that mean? Well, that means that you can run a really large number of processes on your GPU. But there's a couple of downsides. Each CPU on your GPU, on your graphical processing unit, is very weak, which means that if all of your processes are quite intensive and require a lot of computational power to run, then you're not going to get much of a speed up. So the way that this is solved is what you're trying to do is essentially you're trying to run processes that are very parallelizable so that you can have a ton of threads running at the same time, and that's how you get loads of acceleration. But that's also part of the reason why coding for GPUs can be very tricky. Last thing is threading is becoming more and more important to modern HPC machines, both in terms of performance and power efficiency. The reason being, if you get your multi-threading done properly, you can, with a single core, have effectively 2 logical cores, which means you can double your your processing power. And at that point, I think that that is the end of that presentation, and I'll hand over to Arno, who will talk in a lot more depth about what I meant by cores, processors, etc., etc. Oops. Arno?
Yeah, I'm here. Just giving people a chance to catch their breath because I know it's a.
Oh yeah, of course.
Yeah.
And if you please do post your questions in the chat. I'm more than happy to answer them.
Okay, so I mean it's always a bit difficult when presenting. So we've got 2 sides of kind of the situation, as I've said a few times already, hardware and software. And it's always a bit difficult about which way around to present them, because what you encounter first when you use a machine is, well, if it's ready set up and ready for you to use, it's the software you're dealing with. So your way into understanding what's going on is through the software. However, the flip side of that is the hardware, and they're both, of course, tailored to each other. So yeah, we've decided to go this way around to talk about processes and threads and operating system, etc. first. And now I'll tell you about a bit more about the hardware side. So we'll try to clear up in particular some of these terminological niggles that have been nagging us. Okay, so let's see. Oh, right. So what we're going to be talking about is the hardware building blocks of actually not just an HPC system, but a lot of the building blocks that an HPC system has are ones that are common with any computer. We already highlighted the interconnect as something quite specific to HPC systems. So we'll talk about processors, we'll talk about accelerators, both of which are kind of the actual number crunchers of in the hardware terms. We'll talk about memory. Mention interconnect and storage, but we'll mostly talk about processors and memory because that's kind of the most important to know about, and maybe what you have most control over, about how you use it. I'll give a bit of background about sort of a little bit of history just to understand how things have evolved, because understanding also some of the terminology and how these things are designed and put together, it helps if you know a little bit about the evolutionary history, so to speak. So we'll talk about the processor in a bit more detail. We'll see how parallelism happens sort of inside a processor, including multiple cores, including something called vectorization, and including something that we've already mentioned a few times, which are these simultaneous multi-threads, or SMT, or hardware threads are also referred to. Okay, so going really back to basics, what is a computer? Well, this is a computer, believe it or not. It's some jelly that can carry current, and if you measure the voltage at particular places, you can actually use this to solve. Well, I don't want to say solve equations, because actually, if you have an equation that describes some physics, this is actually the real thing. So that this is, believe it or not, a computer which you can manipulate and with using voltages and measure outputs. But that's, of course, that's kind of just to broaden the scope a bit. Is this also a computer? Yes. Don't pay any attention to the silicon chip that's all green with chips underneath that actually makes sense as identifying as a computer. Look at the black slab. That's actually just a bit of foam. Similarly, that's just a material that can do computing. But all joking aside, we're taking a step back just to open up a little bit the idea of what is actually a computer, what makes up a computer. So I already said the basic components and what we'll focus on, but it comes down to it, the sort of generic core, most abstract, most simplified possible model of sort of conventional computing is this: a processor, memory, and probably disk as well. When I say conventional, this is sometimes referred to as von Neumann architecture. You can forget that right away. But anyway, there's lots of different weird and kooky models of how computers are put together hardware-wise. But pretty much all of the computers that you are going to use have adhered to this basic model, which you're not familiar with from your own laptops or whatever you're using. So, processor. What do you mean? What do you mean processor? Okay, so what is a processor? So the terminology has evolved over time and gradually varied as things evolve. Also depends a little bit about whether you're talking about the hardware side or the software side. Sometimes the word processor is used in parallel computing to mean kind of an abstract, a thing that does processing, a thing that executes a task. So that's kind of an abstract concept. But really, when we're talking about it here in hardware terms, as I said yesterday, the easiest way to think about it is a processor is just the thing that you plug into a socket on the motherboard. The motherboard is just the main kind of board in a computer, or in the case of an HPC system, a single compute node that holds together and connects all the various parts that make up one node, that make up one shared memory system. So for example, in the picture shown there, which is not an HPC motherboard, I think it's just some generic motherboard. It has two sockets, none of which contains a chip at the moment. I think they're open. Yeah, so you would plug in two processor chips there. So that would have two sockets, two processors on that board. ARCHER2 is a good example. ARCHER2, the compute nodes there each have two sockets, and your laptop probably doesn't have two sockets, probably just has one socket, so probably has one processor. And that processor is a multi-core processor. And what we mean by cores, we'll see later on as well. So I'm actually going to skip cores just for now, because cores are a little bit more complicated, but I'm going to address the question of what you mean by CPU. Well, CPU is short for Central Processing Unit. Back in the day when we didn't have multi-core processors, we just had single-core processors, there was less confusion about what CPU means, because it was clear that CPU basically meant processor, because so if you had two sockets, you might have two CPUs on your machine. Yeah, Amna, general question. Calculation could be faster if you use more cores and nodes, but at the same time, more core hours will be consumed. How to balance? Oh yeah, yes, that's true. So the balance is, so if something runs 10 times faster on 10 more cores, then that means that it's kind of, in a way, perfectly efficient. So then you don't really care whether then it's never going to be more wasteful to run on 10 cores rather than, to run on 10 times more cores. You get the answer 10 times faster, great. If it's not 100% efficient, and no parallel code is 100% efficient, then you're always going to waste some compute time if you want to run on more cores. However, you have to decide for yourself, and these are almost like How urgent is it? How much compute time have you been granted, allocated? Are you paying for this? How busy is the system? All these questions come into it. But by doing the kind of parallel efficiency analysis that we did in the practical that we showed how to calculate, you can judge and say if something is 50% parallel efficient, that means that you're essentially wasting 50% of the core hours by running at that scale. So then, whether you think that's worth it is kind of a question of cost. So yeah. Okay, just to get back to the hardware stuff. Right, so back in the day when you had just single core processors, there was no confusion really, because if you had two sockets, fine, then you meant you had two processors, which meant you had two CPUs, i.e. CPU meant processor, and you only had a single core on that processor. You probably wouldn't even think about that, having a single core, just that's the processor, that's it. Nowadays, it's a little bit different because we have multi-core processors. So some people might, still refer to that multi-core processor, a single socket, as a CPU, but they mean a multi-core processor which has lots of cores. CPU could also be used to refer to one of the cores on a processor. It could also be used to refer to what has already come up yesterday as a logical core. So the distinction between a physical core and a logical core is that a physical core is an actual bit or an actual accumulation of little bits of hardware. A logical core is actually anything that looks to the operating system like it is some execution unit that it can assign threads or processes to execute on. Now, the most obvious thing is that a physical core is such a unit. So a physical core is a logical core, but as Julian already mentioned just now, something called simultaneous multi-threading, SMT, means that it's processor manufacturers have made it possible for a single physical core, and we'll talk about this in more detail, so I'm not just skimming over this, but we'll get to it in more detail. A single physical core can be addressed as two logical cores, or four logical cores even, sometimes more, but that's rarer. So that's how the operating system sees it. So yeah, the logical core distinction is kind of is an operating system and software level kind of concept. It's about what it can address. Okay, so let's lift the lid on that blank slate of processor a bit more. So let's look inside. So before we just said processor. So let's see, I've got an arrow pointer. Yes, people should be able to see this pointer, I think. So let's look inside the processor. So inside a single core processor, so back in the day when we didn't have multi-core processors, the simplest model of a processor would be that there are a couple of things there. There is something called a floating point unit. We'll talk about this in a bit more detail. So there's something in there which performs floating point operations. Floating point, real numbers, decimal points, etc. So these do maths with real numbers. So that's the actual bit that does the number crunching. The cache is a little bit of memory. So you need to store a little bit of information close to the bit that's doing the number crunching because it needs data to act on. And there's reasons, as we'll see later, for storing this close to the floating point unit. And indicated here, 2.2 gigahertz is indicating a frequency because there is processors operate according to a clock. So there is so processors, what they do is they execute instructions, because ultimately all software is instructions, and they do this according to a clock. So during every cycle of a clock, a number of instructions are executed. So the basic functionality of a processor is that, as I said, it executes instructions, and the ones that we really care about in lots of scientific codes are the kind of numerical arithmetic or math operations involving integers and especially floating point numbers. Okay, and so these are performed. So what needs to be done to make that happen is that data that's stored in memory needs to be brought to the processor. And also results need to be fed back into memory. And then there's basically a stream of instructions that are fed to the processor. When a thread or a process is running on a processor, then it's basically that processor continuously being fed instructions to execute. So registers is simply another word for the local storage of information data close to the processor, and these can store only small amounts of data, so maybe about 100 values of integers or floating point numbers. So I already said the clock speed is a key characteristic of processors. They determine to a large extent how fast they are, and or how fast a single core is, I should say. And also the float, as a result, the peak floating point capability, namely how many operations involving real numbers, involving floating point numbers per second, can a processor execute. These are key aspects of speed. So when it comes to the units, so we already talked about a floating point unit. So inside a processor, inside a single core processor, there are a number of different functional units. We already mentioned the floating point unit. So we have also an instruction unit, which is responsible for actually getting the instructions for the processor to execute, decoding what they mean, and then assigning them for it's kind of weaving them together to actually feed into the processor. And yeah, there's a lot of detail about here, but basically it's also, it's involved in scheduling these instructions. Then there's an integer unit, which handles integer maths, addition, multiplication, division. It's also sometimes known as the arithmetic and logic unit, or ALU, because there's also logic associated with this. Or also the floating point units, which does maths with real numbers. It's a key thing, and the floating point performance is really key for processors for high performance computing. Some other things, software does different things depending on values of particular variables that are in the code. So there's logic in the code, and so there's some unit in the processor that determines which instruction should be executed based on the. So sort of logic means that there are branches, different based on a certain condition being true or false. There's certain branches of code execution that take place. There's a load and store unit, which is responsible for loading and storing data to and from memory. And there's all kinds of further details, which I don't want to burden you with, but basically the processors are complex things. There's a lot to them. So let's look a bit about to understand kind of where multi-core processors come from, as well as other aspects of processor design that influence performance and are useful to know about. Let's have a little bit of a quick look at that evolution of processors. So there's something called Moore's law. So processors are electronics chips. These are based on manipulating the voltage and currents to make zeros and ones that basically are the root basis on which everything else is built, all the instructions and the logic to execute these instructions, etc. So it comes down to tiny transistors. And Moore's law is just an observation stating that over the past 40, 50 years, however long, the number of transistors, the technology to fabricate processors has improved to in such an extent that we can keep on making chips smaller, design them smaller, fabricate them smaller, such that the number of transistors per nanometer squared, say, doubles every 18 to 24 months, and that has held kind of true, but it's decreasing. My question is, how do you build better? How do you build better processors over time with that? How have processors improved? How have they changed in the past 30, 40 years, whatever? Well, in the so-called good old days, over the course of about 3 decades, processors were becoming more complicated. More units, etc. But it was clever, but also in a very simple way, the clock speed kept on increasing. So you could wait a couple of years and you buy a processor that has twice the clock speed or 4 times the clock speed, and your program will run twice or 4 times as fast without having to do anything else. And that was great because the clock speed doubling simply means that the same processor could execute twice as many instructions per second, i.e. your software runs twice as fast, which is great. So, but that stopped being possible to simply keep on pushing because there are fundamental physical limits to the amount of power being generated, power needed to feed the system, and also the heat being generated by a system like that, by a processor like that with higher and higher clock speed. So the clock speed stopped increasing, essentially. They just kind of hardly increased any further. So currently they're around 2 to 3 gigahertz. So clock speed is a key aspect of processor performance. As we'll see, there are other ways of other aspects that determine processor performance. But yeah, so there's some instructions, integers operations on integers can be done in parallel with operations on floating point numbers because these are two separate number crunching units. So in principle, if you're doing both kinds of things, then they can be done at the same time. So you can have a bit more operations per second, but essentially the clock speed is a big determinant. There's also all kinds of clever things where instructions are executed in different order, and the processor tries to do really complicated things about guessing what instructions are coming next, already computing them, and then giving the result of one of them, one of these branches of execution. But that's all details. So the question was, as it became possible to keep on having more transistors and design processors to be more complex, but not increase the clock speed, what are other ways that were used to improve the performance of processors that are relevant to HPC now? So the first one is something called making use of vector instructions or vector operations. It's also called vectorization. The basic idea is that if you have, as many scientific codes do, some vectors, an array, or which can be one-dimensional, two-dimensional, three-dimensional, however many dimensions, of floating point numbers, for example, and if you wanted to perform the same operation on many numbers at the same time, because that's the idea. But the idea is if you have a single instruction you want to execute on lots of different values at the same time, you have a situation where you have a single instruction on multiple data, which is short for SIMD. So you can actually do this really efficiently. So the processors have been designed to do this efficiently. As follows. Well, I'll just summarize. So SIMD is one approach. Producing multi-core processors is another approach, and providing multi-threading or SMT within a single core is another approach. So the first approach, SIMD, or vectorization, the examples here, where a single instruction can add these 4 numbers. Rather than having 4 instructions that each add 2 numbers, you have one instruction that adds these 2 sets of 4 numbers. So in principle, if that can execute in one go, that could give you a 4 times speed up. And processor cores have been designed to do this very efficiently, to store the data, to store those 4 values or 8 values, however many there are, and to add them all at the same time. That the number of instructions that can be encoded to take place at the same time is known as the SIMD width, or the vector width. So the second kind of processor performance improvement is multi-core processors. So there, the idea is that so if you have twice the number of transistors, then you either build twice the clock speed, which is no longer possible, as we said, or you could actually build just 2 processors, build more processors. And the second option is more power efficient. So when I say build 2 processors, actually, what you do is you build, so you replicate 2 processors, but actually you put them both on the same chip, because then that means that they can share some caches, and they can share some elements, which means that it's faster for them to access each other's caches if threads are running on both of them, or processes are running on both of them, and it's also cheaper. So this is basically the birth of cores. Having 2 processors, as I just outlined, share a chip and share some of the elements like caches and even some functional units like maybe a floating point unit or some other units. Those are cores, and that's essentially what a multi-core processor is. So this is the anatomy of a single processor, a single multi-core processor, where each of these 4 cores is the same essentially as the entire single core processor that I've depicted before, except for this shared cache. So you can see internally each of these cores has its own cache, but there's also a shared cache, and cache is just a little bit of memory, right? So they have a little bit of memory that's just unique to them, but they also have some shared memory. So that's both good and bad. Good because it means they can access each other's memory, which can be quite efficient, but also they're accessing each other the same memory, so there can be contention for that, which I'll explain in a minute. So the idea that we have, sort of the model that we have here, is that there's a hierarchy of caches, and this fits into a more general hierarchy of memory, stretching all the way from main memory down to different levels of cache. The L stands for level. So here you can already see the terminology creeping in. Here CPU in this instance means core. So we've got individual cores, all part of one single multi-core processor. They each have their own individual L1 cache. So these are the innermost caches that I showed in the previous diagram. Then they have some L2 cache, which which is maybe more quickly accessed by each of them, but can be shared by the other ones. And then they have an L3 cache to which they which they can all access and probably access with the same kind of speed. And these increase as you get further away, lower down in the picture. These different levels increase in size of how much is stored, and also decrease in how fast it is to get data from it and to read data to it. Same goes for main memory, which is much bigger, but takes longer to read and write from and to. So some of the advantages with sharing caches is that you can communicate with threads or processes on other cores quite quickly, but also you share the space, so it might be capacity issues and that needs to be managed, which has additional overheads. On the other hand, if there's only one core running, okay, that gets to use the entire cache. Another thing that's shared between cores is which could be a limiting factor, is that the bandwidth for communicating with other processors is shared, and as well as the connection to the main memory. So the second key thing of interest is the simultaneous multi-threading (SMT). So this is where essentially the same. So it says same processor, but it should really say same core here, because this would be in reference to the single core processors. So the idea with simultaneous multi-threading is that multiple cores can a single core can run multiple streams of instructions at the same time. For example, at the same time as loading data, as multiplying two floating point numbers, it could be loading data from memory, and it could also be doing something with integers. Now, this means that some replication of hardware is needed, but everything else can be shared between these streams or between these threads. So the idea here is that a single physical core has a number of different functional units, etc., and it can execute more than one stream of instructions at a given time. And in other words, it can execute more than one thread or more than one process at a given time. So these are sometimes called hardware threads, but it could be threads or processes. And these appear then to the operating system as distinct logical cores. In other words, if a core can execute two instruction streams at the same time, then it would have two simultaneous multi-threads, and it would appear to the operating system as having two logical cores corresponding to that single physical core. So, for example, the AMD EPYC supports two cores. To have an idea about what it looks, so if you had two software threads, two streams of instructions that your software wants to execute, the red and the blue, these could either be executed on two distinct physical cores, and then some of the units, so the different columns here would be, for example, different. One of the columns could be floating point units doing floating point operations. Another column could correspond to integer unit operations, etc. Then the other picture on the right-hand side is if you have a physical core that supports SMT, so it can at the same time execute the instructions from both of these streams if SMT is enabled, so pack things together. This can be successful. It's not always advantageous. Speed up is sometimes limited. You might get some benefit, especially that you are unlikely to get any benefit if both threads or both processes are trying to do floating point operations, because then the limiting thing is the performance of the floating point unit, which they if they share that unit, then it's not going to be any faster than just having one thread running on that physical core. For some cases, it can even cause a slowdown because those threads are competing for bandwidth, they're competing for cache. So yeah. So I'm aware that I'm running a bit short on time. So let's see. I will speed up a bit. So for the processors on ARCHER2, you can look back and see that there's some data here about the vectorization possibilities and the SMT possibilities and the sizes of the caches and the relative speeds in terms of how fast they're accessed. It's just for information. So we already talked about NUMA regions and how these can influence the speed with which threads running on some cores in a different NUMA region can access data that's in another NUMA region. So this is another reason why software that does parallel computing with threads can sometimes be slower if it's trying to do that. So when it comes to accelerators, so we talked about processors, but accelerators, GPUs, for example, are also very important for number crunching. So they're a way of offloading really heavy calculations. So the idea is you plug in a separate device, separate card to the motherboard with its own cores. It's very widespread. ARCHER2 doesn't have GPUs, but they are increasingly common on big HPC machines. And they have large numbers of relatively simple cores. They're nowhere near sophisticated as the multi-core traditional multi-core processors by Intel, for example, but they have a separate memory, and they simply have thousands of cores which can perform relatively simple operations. They can crunch through these operations. So you get very good performance, actually, in some cases. I say some cases, you get very, very good performance from these GPUs if your code is doing lots of floating point operations on arrays, on matrices, things like that, which is quite a common thing in a lot of scientific codes. So the only thing is that they do present an additional complexity in the memory hierarchy. So accelerators have their own memory, so sometimes it's necessary to move data to and from the GPU memory in addition to the main memory. This can introduce additional overheads. And the software can be tricky to program and can be a bit tricky to use, perhaps. Just visually, and these are some older examples, but if you look at the hardware, the actual chip, this is a traditional multi-core 12-core CPU. It's not the AMD EPYC. You can see that the purple area is the space dedicated to floating point operations. If you compare the same to, again, quite an old GPU, there's much more higher percentage of the space is dedicated to floating point operations. So a bit about memory. Memory is also very important for the performance of computers, in particular in high performance computing. And the performance depends on getting data to the processor quickly, and then also getting it from the processor if it needs to go somewhere else. So there's two aspects to that I already highlighted from a kind of physical perspective or hardware perspective. It's latency, which is how long it takes, how long a thread or process needs to wait until the data starts to arrive for it to consume. And bandwidth is the amount of data that can arrive per second. It's like a hose, like how much data can you get per second. So in that sense, just to get a sense of, if a software is trying to read from disk, that's very, very slow. And you have to wait much longer than if you're reading something from memory, from RAM, from main memory. Memory is faster, but it's limited in size. So you can't have nearly as much as you can have in files on disk, and it can still be too slow. The caches are much faster, and all the levels are increasingly fast, but they're much, much, much smaller. So there's kind of this hierarchy there. So this shows an overview of that. Smaller capacity, means and higher cost, and in terms of number of processor cycles that need to wait to get access to data from each of these parts of the memory, and the expected bandwidth that you could get in terms of per second. Oh no, sorry. There's this on the right hand side is the size of the memory. So to give an overview, so apologies for running a bit late into our lunch, that you hopefully now have a better idea of the key hardware components in computers in general, but especially in HPC. I've not talked about the interconnect, not really talked about disk, but processors, accelerators, and memory, which are key. So whenever we're looking at performance and running software, we think about if it's slow, why is it slow? It could be because, well, the floating point performance of the processor simply isn't strong enough. So, but actually often it's the case that the problem is memory. Or rather, maybe it's the amount of memory, but maybe the amount of memory at a given level. So not enough of the problem can fit into the cache, for example, which means that it's slower to get that memory to the actual number crunchers, namely the processor and accelerator. If you're reading from disk, especially, that can be really slow. Finally, depending on the interconnect performance, the communication between parts of your program can also be a limiting factor to performance. So often for many current codes that are the really large scaling ones, often memory bandwidth or in some cases communication are limiting the performance. And just to go back to Julian's talk about the performance and parallel performance and all that stuff, the Amdahl's law, that's all theoretical. So Amdahl's law tells you something about the theoretical optimal, even if there are no overheads apart from the having the serial fraction of the serial part of the code. But there's all these things that are limiting performance. So it's no surprise that scaling isn't perfect. Okay, I'll leave it there. Apologies for going over time. So any question I can answer in text, in chat during the break, or pick up later. Thanks.
Hey everyone, I hope that everybody had a nice lunch and a nice break. And please could I ask, as with the start of every one of these sessions, could I ask for a show of hands to get an idea of how many of you are back, please? Okay, yeah, so definitely, we're definitely correct at this point. So for the first session this afternoon, and indeed for another session this afternoon, we will be doing a GROMACS practical. I will put a link. I will put a link to the course material for this practical session in the chat. The idea of this practical, the purpose of this practical session is to benchmark the performance of GROMACS with a very well-known small benchmark. In this exercise, the hope is that you'll be running GROMACS molecular dynamic simulations and benchmarking how efficiently a small system of roughly 80,000 particles runs as you increase the number of processors to do the task. So the smaller runs can take a while to run, so it's probably best to start quite quickly, but I'll give you a wee bit of detail about the benchmark itself. The benchmark is called BenchMEM, and it can be found at this link here, unless I've mistyped it, but yeah, it can be found at this link here, and this is a a research group at the Max Planck Institute who do a number of GROMACS benchmarks, as well as giving some really interesting, they've done some very interesting research with GROMACS. The benchmark has been used in a number of publications, one of which I've linked to here. And roughly speaking, the benchmark simulates a membrane channel protein, which is embedded in a lipid bilayer surrounded by water and ions. And as I said, the size of the system is roughly 80,000 atoms. I've got instructions for how you can get the benchmark. There's also, I have uploaded it to, I've uploaded it to, if you go in /work/TA017/shared, /gromax practical, and I'll put that path in the chat. If you go into that directory on ARCHER2, you should be able to see that there's the bench mem.zip, which is there, as well as an example Slurm submission script. In case you want that, the other way you could get your Slurm submission script to work is by just copy and pasting the one that we've provided here. The Slurm submission script is exactly the same as before, except you'll notice that here, where for tasks per node, I set that as 1. And the reason being this is the test script for running on a single core. And hopefully during this tutorial, during this practical, you'll be running a number of jobs and increasing the number of cores. So from 1 to 2 to 4 to 8 to 16 to 32 to 64 to 128, and then even try maybe on 2 or 4 nodes to see whether it runs well. Bear in mind that, so you should be able to just change sbatch -- tasks per node from 1 to 2 to 4 to whatever. And bear in mind that if you're wanting to use more than 128 tasks per node, so for the 256 and the 512, you will need to increase your number of nodes. Now, I thought it would be fun and a good idea, and I hope you'll agree, I thought it would be fun and interesting if everyone then put the solutions they got for various core counts in the Etherpad, and then from that we'll get an idea of like if anyone's not been able to run the full set from 1 to 512, then hopefully there'll have been some people who maybe were more interested in running on more nodes, more people, and some people in the middle, and things like that, and then maybe we'll be able to see an overall solution for the group. And I'll definitely be putting my results in as I get them, and I hope you do too. I'm here to answer the questions that come up, as are Arno and Holly. And other than that, I will come back in about 15 minutes to see what we got in the Etherpad and to have a look at the results and talk you through the solutions and the interesting things about this. Hope that works for everyone. By the way, everyone, something that I've noticed is the submission script that I had uploaded uses the short queue. If that queue gets a bit too busy, you can always use instead, I'll put this in the chat and in the Etherpad, you can change the QoS to standard and use the reservation for today, which is TA017_139. That's it. One thing that I forgot to mention, for those of you who are unfamiliar with GROMACS, sorry, I'll share my shell real quick. That was rather poor of me to you would all be happy with GROMACS. When you run GROMACS, one of the files that gets output is a file called md.log. And if you look at md.log, I've moved them to like the number of processor core counts. But if you look at md.log, you get the last output, which tells you who's written or taken part in the which tells you who's written and taken part in GROMACS, copyright information, lots of information about how it's split up, what you should cite, what inputs you're currently using, and then information about your run. And then eventually, right at the very end, it gives you these 5 lines, which are fantastic, which tells you the time. The core time is the total core time that's been used to run. The wall time is the real time, as in the clock time that's been used to run. So the wall time should be equal to the core time divided by the number of cores you used. percentage, I imagine, is the speed up, but I'm not too sure. I never checked. And then underneath it gives you the performance, and it tells you if you'd run this simulation for an entire day, how many, you would have run 117 nanoseconds, and you would have been getting 1 nanosecond completed every 0.2 hours. So when you've got your LAMMPS output, you can just do tail minus n 5, and then the log file, md.log, it would be for you, to get the, it would be 6 rather than 5. My apologies. 6, to get all of the performance information that we're after. I will copy that into the chat. There we go. I'm happy to see that there's been some people who've been adding some performances as well. I'll keep going for mine. What was I going to say? If anyone has any results for 2 cores, 4 cores, 8 cores, and 16 cores, that'd be grand. I should have results for 64 and 32 as well. And in about a minute or two, I will chat a bit more about this exercise and show you what I've been up to. As always, please ask your questions in the chat or in the Etherpad. We're more than happy to answer. Right, well, thank you everyone for putting your answers in. Let's have a quick look at them. Anyone, I ran them the wrong way around, so I started with the big system and then ran the other way around, the assumption being that if everyone's launching jobs at the same time, bigger jobs will be harder to run later on. But it looks like we've got solutions for everything except 8 cores, but I've got an 8-core system running in the background now, so hopefully we'll get a result for that as well in a sec. And what do our results look like? So what have we got? We've only got 1 core system, and that looks like that ran in about 300 seconds. And would have run 2 nanoseconds per day. The 2-core system we have also ran in 300 seconds, but the performance seems to suggest 8.149 nanoseconds per day, which to me means that probably instead of wall time, you output the total core time, but maybe not. Next, 165 seconds to run 4 cores. Oh, we do have an 8-core. Brilliant. 94 seconds for the 8-core. My 8-core is still running after. Oh, there we go. It's finished. Tail. Yeah. 94. Yeah, I've got 95 seconds and 18 nanoseconds per day for the 8 cores. Performance I got as 18.81 nanoseconds per day. I keep clicking the wrong link. There we go. And then 16 cores we've got. So I'm really confused as to the 305 seconds of wall time for the 16 cores. Maybe mine is wrong. But I got a performance of about 35 nanoseconds per day. And then it sort of starts to slowly, the changes, the improvement in speeds very quickly decrease as you go down from there, because essentially this is still quite a small system and you're running on many processors. So what I'm going to do for the next 2-3 minutes is I'm going to show the solution that I used, the code that I used to run my simulations. And then during the next session and during the break, I believe Holly will be giving the lecture that's coming in a sec. I will use all of this data that you've given me and compile it and show you the final performance graph that we got together, and I'll show that at the start of the next GROMACS practical. Does that seem sensible to everyone? I will take resounding silence as a yes. Right, so what did I do? I've already briefly mentioned that I made sure to save all of my files based on the number of cores that I was using. So 128.log is the mdlog file for 128 cores. This is just a general idea so that I can refer to them and show you the results and check that I've not output the wrong results. And indeed, if I tail that, you'll see that I had a wall time of 14.7 and a performance of 117 nanoseconds per day, which is what I wrote down. To do those, I didn't really alter the submission script too much. For the larger runs, I increased the number of nodes to 4 nodes for 512, 2 nodes for 256, and 1 node, and then everything else was done with 1 node. So it was 4 nodes for 512, and I also made sure to raise that to 128 tasks per node. Then the rest of my submission script is exactly the same as the one that was given. And then at the end, just to save myself time, I did a move md.log, which is the output log file. And then I would edit this to, in this case, it would be 512, because I'm running on 4 nodes and 128 cores per node. And then I removed the other files because they are extraneous and we're not using them in this exercise. And one last thing, which was, oh yeah, and I don't like the fact that GROMACS keeps track of every single log file whenever you run a second run. That's just a personal preference. I'm sure that it's really nice having all of these backups. So quite frankly, this is the simple solution to running these. I heard that there was a question in the chat. I'll answer the question before passing off to Holly. We don't want to mess with CPUs per tasks ever. So that's a great question. We will be messing with CPUs per task for the next practical session, for the next GROMACS practical session, which will be after Holly's lecture and after the break. And there we will be entirely just messing with CPUs per task, which will also be quite fun to do. Right, with that, I'll hand over to Holly, unless there are any other questions. And as always, if you have any questions or if you realize later on that you've got any questions, please ask them. I'm more than happy to answer them. And with that, over to you, Holly.
Hello, everyone. Okay, so I'm just going to share my screen. You might get the infinity tunnel. You are. Okay, can everyone see that okay? And I've lost it.
Yeah, it looks good when you don't have the tunnel.
Okay, tunnel is gone. Yeah. So yeah, I'm going to discuss parallel programming models. So this will touch a bit more on the idea of processes and threads, which we've discussed before in the software lecture. But this is going to go into a bit more about how these are actually used in HPC applications and how we get parallelism from them. So yeah, this is going to touch on shared memory parallelism. So we've already looked at threads and a little bit about OpenMP, I believe. So we're going to look at this a bit more and talk about how actually shared memory is used within codes to exploit parallelism, and also how it's actually used in HPC machines. And this will relate a bit more to HPC architectures and how we go about running with OpenMP on an HPC cluster. I also go on to mention message passing parallelism. So this is a kind of distributed parallelism where you have processes spread out on their own separate CPUs. So this is what we've just basically been run with in the last GROMACS exercise. We'll also cover MPI, which is a library used for achieving this parallelism. And then again, look at using this on HPC machines and how this kind of relates to the architecture and the structure and how you actually run and exploit this parallelism. I'll then cover hybrid parallelism, which is a combination of shared memory and distributed parallelism, so a combination of MPI and OpenMP. This will actually be touched on in the second part of the grammar exercise, and then a bit more about GPU parallelism. So on to shared memory, which is associated with using threads. So you have an idea of having, say, like a parent process and then some data which is associated with it or stored on it. Then in shared memory parallelism, what you can usually do is kind of spawn a parallel region where you have multiple threads. So here you have 2 threads. And then what happens is this data is shared between them. So they can all see the whole extent of the data. And then a nice way to exploit parallelism in this case is if you have each of these threads has a core associated to it, they can then work on, say, half of the data each. So you're kind of sharing this data amongst them and then decreasing the amount of work that is done on a thread as opposed to if you were running with a single thread. In shared memory parallelism, the threads can read each other's data. So for example, here, if these threads were doing some kind of operation along this array, and the first process needed to see what was in the in A4, which is on the second, first thread had to see what was on 4, which is on the second thread, then it could just simply read this data. So it's a really nice way of having the communication kind of implicit. Threads can just read different parts of the data, and you don't have to worry so much about communication. So it actually makes programming with threaded parallelism or OpenMP fairly simple in that kind of way. So a good analogy for this is if you have 2 people working on the same problem within the same office, and if they have one large whiteboard and they're both working on this problem together, so you might imagine that they decide to split this problem in half, and they can work on this problem separately, but then they can communicate with each other about what they're working on and the parts of the problem they're solving by writing onto the shared whiteboard. So they have this shared idea of having a shared space where they can communicate with each other and also work on the problem. So yeah, this is just like having 2 threads running on different cores attached to the same memory. So these people are working together, they are collaborating, but not interfering with each other. And you also have the idea of them having their own private data. So if they're working on something independently and they don't want other threads or other people to interfere with that. So communication between threads is just done through the shared memory space. So you can imagine one thread could write some data into the shared memory space, and then a second thread could come along and then just read that data. So for example, here you have thread 1. It has its own value of A called myA, which it sets to 23. And then this is like its private space. And then it can then update a global A called A to be equal to myA. Later on, thread 2 can come along and read this global value of A and then set it to some value in its own private space called its myA. And myA in this case are going to be different because it's in their private data space. But yeah, this is just a simple way of how threads can communicate between each other. It's actually a bit more complicated than this. And you also have to worry about synchronization. So for example, if thread 2 came along to read this data in A before thread 1 had written anything to it, it might just get a load of garbage or might not get what it expects. So yeah, thread 2's code must execute after thread 1. And you actually have to worry about synchronization. This is quite important when you're programming with OpenMP and can make it quite difficult sometimes. So yeah, usually you have like forms of explicit communication such as barriers and locks on variables to ensure threads are reading and writing the data in the right order. So yeah, I've mentioned a bit more about OpenMP. So OpenMP is an API or application interface for shared memory programming using threads. It's one of the most commonly used ones. Can think of a few others. So yeah, you can expect OpenMP to be used in all compilers on all HPC platforms. You've already, maybe you haven't, I think it's coming up in the next GROMACS practical. But yeah, usually to compile a code with OpenMP, you just need this flag here. For example, with GCC, it's -f OpenMP. And then that allows the use of all the kind of OpenMP parts of the code to run properly. So the parallelism is implicit. A lot of it's extracted from the programmer. We'll get to an example of this in the next slide. So you kind of just specify which parts of the program you want to run in parallel, and then the compiler goes away and produces the parallel executable. So a good example of this is loop parallelism. So if you've got a loop within your code and you want to run this loop in parallel, so you want to kind of divide the work in this loop between the different threads. OpenMP has this way of doing parallel pragmas, so pragma OpenMP parallel, and then you set whether variables should be shared or private, which shouldn't worry too much about right now unless you're doing any programming with it. But yeah, you set this pragma OpenMP for, and what it will do is it knows how many threads are being passed into the program, which is set by an environment variable. And yeah, once it knows how many threads, it can just take the number of iterations in this loop and then share them between the number of threads you have in the program. So this allows it to parallelize the loop automatically. This is quite a nice thing to use. It's quite simple if you're a programmer to go and stick a load of these in. But yeah, you have to worry about if you've got quite a simple case of if you have quite a simple case where you don't have to worry too much about synchronization of variables, and you know all these variables are kind of independent of each other, you can add it in quite easily. So how does using threaded programming work on a hardware level? So we've just said a lot recently in this course that you can't really use, well, you can't use OpenMP or threads beyond a node. And we mentioned this is because of they're on the same operating system, so threads need to be associated with the same operating system. So we're naturally limited when we're using threaded parallelism to a single node. So this picture here is a single node on Archer. This is comprised of 2 sockets, and then there's a variety of different memory regions as well. So these 8 NUMA regions of 16 cores. So yeah, you don't need to worry about this too much, but you need to be slightly aware when you're running OpenMP that you want to keep the threads within the same memory region, because you can have them, you can make things a bit slower if you're accessing memory from a different memory region, basically. So you don't want to span threads across multiple memory regions usually. So you're kind of restricted to only a few tens of threads on most machines. Yeah, and yeah, that's kind of limiting for shared memory parallelism. So to use this, you have this environment variable called OMP threads. So this is usually set in your job script before you run like srun, before you launch it. So here you set this environment variable to the number of threads you want to use, and then this is used within OpenMP to find out the number of threads and do all the parallelism. Someone mentioned earlier about this SBATCH option, CPUs per task, and do we want to ever mess with it? So on ARCHER2 in Slurm, this should be set to the number of threads that you're trying to use. So when you call this is the number of cores it's allocating to a single task or process, and it should be the same as the number of threads to ensure that you're getting 1 core per thread, and that the placement within the within the node and processes all works out correctly. So now I'll say a bit more about message passing. This is kind of distributed parallelism where you're using processes. So each process has its own kind of memory portion. So kind of comparative to the previous picture we had with shared memory parallelism is if you have, say, a kind of problem that you have, say, an array of data and you want to do some operation on it. In distributed memory parallelism, each process gets like a distinct portion of this array, and they might not necessarily know anything about how the data was arranged on the, well, they wouldn't know on the like previously, so they know what's in their own domain of data. So here you have two processes, and one has been allocated the first chunk and the second has been allocated the second chunk, and then they can go away and do their work on this. So the data is divided up between the processes. They can only see their own data and any communication. So if process 0 needs to work out what data is in process 1, all this communication needs to be done by messages. So this is sending and receiving of data between the processes. So a comparative analogy for this one is if you have two people with two whiteboards, but they're in different offices. So they're both working the same problem, but they're isolated from each other. They don't know what the other person is working on necessarily. They have to communicate with each other to know what's going on. So in this case, they would have to have some kind of way of communication. For example, here it uses a telephone. One can ring the other one and say, I'm working on this bit of data. Or it can ring the person and say, what bit of data do you have in this location, etc. And then they can communicate. But this communication is explicit, so they have to actually, like, be done within the code, and they have to make the effort to use the telephone. So in processes, this communication is done by explicit messages. So you actually have explicit sending and receiving of data in the code. In this case, it's two-sided. So process 1 will have to send the data, and process 2 will have to do a matching receive call to receive the data. So it kind of starts off with process 1 having this data. It says, I want to send to process 2 this data in A, and process 2 will receive this data. It has to do a matching receive call, so it has to say, I want to receive data from process 1, and then say where it wants to store it. So it's storing it in B, and then once it's issued this receive, the data is received. And this counterpart receive counterpart must match the sender process number. So it's very explicit. And the kind of hardware that fits in a distributed model. You have processes which are distributed across multiple nodes. So you want to usually assign one process per core, and then you have, on modern machines, you'll likely have many cores on a single node. And then messages go across the interconnect when you have to communicate to a different node. So internode messages are fast. So messages between processes on the same node are usually quick because there's no real interconnect. They're just within the same kind of memory space. But then you have to worry more about your number of across node messages between nodes. Message passing is the standard parallelism for most modern machines, as it can exploit cores across multiple nodes. So we're not limited at all to a single node. We can use all the cores within a node and then use message passing to communicate across nodes as well. Yeah, and so the message passing interface, or MPI, is the library which is used for writing parallel programs which use this message passing model where you have to send these communications between processes. There are a lot of different implementations, but they all support the same MPI standard. So the code that you'd go away and write would be the same for all of them, or nearly identical. So some examples of this are Cray MPitch, or MPitch, or yeah, we have Cray MPitch on ARCHER2, OpenMPI, which is open source MPI, and Intel MPI, which is the Intel variation. So in message passing, all the parallelism is explicit. The programmer needs to decide themselves how they're going to decompose this problem over the processes. So as Arno mentioned yesterday, when you're talking about parallel models, maybe if you want to do a grid-based decomposition, you have to worry about the decomposition and then also sending and receiving data between processes, especially when you're talking about like grid boundaries. So you have to worry about how your problem is being decomposed, and then that fits in with the communications pattern. And yeah, you need to decide what to receive and when, and kind of how often as well, because communications usually become quite an overhead as well, especially as you start running more and more processes. You want to only communicate things when you need them. So within MPI, there are different types of communications. So we have point-to-point communications, which is in the example I showed earlier. So this is just a message sent from one process and received by another. So simple going from process 0 to process 1, say. So this is a simple send and receive on the other side. And you also have collective communications. So these involve all the processes. So, well, all the processes within a certain group, which is called a communicator. So for example, in this case here, you have a process 0, which is broadcasting a load of data to the other processes. So this might be something you want to do at maybe the start of your calculation if you're spreading out a load of data. Yeah, what actually goes on here is way more efficient than what I've illustrated. So this is quite a poor way of doing it because you're still sending 4 messages. But what they do, these collective communications are optimized very well to be efficient. So they'll try and minimize the number of messages that are actually sent between all the different processes. So it's much more efficient than doing many point-to-point messages. So it's always advised if you want to send data lots of places, you should be using collectives rather than point-to-point communications. Yeah, so as mentioned in MPI, one process is associated with one physical core. And yeah, when you run in your job script and you use your job launcher, such as srun, MPI run, or MPI exec, this then launches the kind of same program across all these processes. And it will take information either from your batch options or your options which are supplied to the launcher to know how many copies of the program needs to be created. So for example, your number of tasks per node or n tasks, which are set in your batch options, can be used by the launcher to know how many copies of the program need to be created and how to place them. Okay, so now I'll cover a bit MPI and OpenMP. So this is a combination of both of these things. It's kind of a mixed mode parallelism. This is becoming more widely used within applications and kind of more, in some cases it can be more performant and more useful and used for kind of extending the scaling of codes. So what is this hybrid of MPI and OpenMP? So if you imagine a kind of modern machine, they're distributed clusters. So you have a node with multiple cores on it, and you have multiple of these nodes. So what you want to think about is using shared memory within a node and then MPI between nodes. So you kind of build up a picture of having sort of OpenMP used within a node, and here you can have like a process that spawns multiple threads, and then when outside of this kind of parallel region, you can use message passing between the nodes. So you build up this kind of picture. So this is known as MPI plus OpenMP. So you're using the OpenMP within a node, not necessarily the whole node, usually a subsection of the node, and then message passing between each of these kind of processes where you've launched multiple threads. It has the possibility to improve the performance. This is because you can get message aggregation, so you end up sending less messages overall in this model, and particularly less inter-node messages can help improve the performance. It can also decrease the overall memory requirements as well. So you end up with less copies of data on the node. You can imagine having just one copy per process rather than having multiple copies on each thread, because the threads are sharing data. Why would they need to have their own copy of it? So this can help reduce the memory requirements. So yeah, a bit about the usage. So yeah, OpenMPI and OpenMP is implemented in lots of HPC applications. It's not always more performant than using a single thread, e.g. pure MPI everywhere. So this kind of is usually due to the implementation of the model within the code. So if you start with a pure MPI program and you start putting in OpenMP into it, you'd have to add quite a lot of OpenMP in different areas in order to get performance within the whole code. So it's not always more performant than using a single thread. And the number of threads that you use needs to be tuned again to the use case and the machine. So this is something you want to look into when you're running your initial scaling tests. If you're using MPI and OpenMP, you want to check the different number of threads and find out which is the most performant for your particular use case, and the machine as well, because machines have different hardware, and this will relate to which number of threads is best. And then, you also need to be aware of the underlying node structure. So I think this will come up in the next GROMACS practical. But basically, you want to ensure that again, like with OpenMP, you want to ensure that groups of threads are on the same NUMA region. Otherwise, they can be accessing data from a different NUMA region, and this can slow it down. So whenever you're running this model on an HPC machine, you need to be very aware of the underlying node structure. So you need to think about the placement of the processes and threads on the node architecture, and ensure each thread is placed on a separate core, and then that you're populating the entire node properly. And then to do this, you'll want to set the number of processes times the number of threads equal to the total number of cores, right? So you have each process will spawn n threads, and then if you times these numbers together, it should equal the total number of cores on the machine to ensure that you're optimizing the full machine properly. And as mentioned, they should not span more than one region. This will be in the exercise. Final word on GPU parallelism. So this is using GPUs to get parallelism. We've already touched on this a bit earlier on in the course. So using GPUs is ideal for some HPC applications, as they're designed for doing many numerical operations at once. So you have many threads on a GPU, like many cores, doing lots of like little operations they can do at once. So this is a good fit for stuff like molecular dynamics, when you have lots of numerical operations that you're trying to do at once. And it's ideal, of course, to execute the same operations on different subsets of data. So numerically intense calculations can be offloaded to GPU, so specific parts that are quite intense, and then the rest of the code can be also run on CPU. The GPU memory is separate from the memory of the main host. So if you're wanting to run something on a GPU, you have to copy the data on and off the GPU from the main host. This incurs a bit of an overhead, so you obviously want to minimize the number of times this is done. And the application can run on multiple GPUs per node, so and on many nodes. So yeah, you can communicate between different GPUs on a node using MPI, and then NVLink enables fast communication directly between GPU memory spaces. So onto some different ways of programming GPUs. For NVIDIA GPUs, CUDA is the common language used for programming GPUs. This is a proprietary NVIDIA software, so it's available on systems with NVIDIA GPUs. So yeah, in this case, you're rewriting the intensive code as a GPU-specific function, which is called a kernel. And then it also includes functions for copying the data on and off GPU to CPU. You can also do GPU programming within OpenMP. So there's a syntax for offloading OpenMP threads to GPUs. And there's also the HIP HIP, which is a kernel language for NVIDIA and AMD GPUs. So this can convert the CUDA code to HIP, which can increase the portability. So a bit about scientific libraries. So libraries are used in lots of HPC applications, and these contain optimized code for doing very particular functions. So, for example, common mathematical routines. You have dense and sparse linear algebra. So libraries such as BLAS and LAPACK, and first Fourier transforms. So, for example, FFTW, some of you might have heard of. And yeah, parallel MPI and thread-based versions of these libraries are available. And yeah, these are critical for the use of performance of many large-scale HPC applications. So these are incorporated widely through various HPC applications. They can also include parallel I/O, which is reading and writing large amounts of data quickly in parallel. And recently, there are versions of these libraries that offload to GPU and use CUDA. So to summarize, discussed a bit about shared variables parallelism. So with OpenMP, so this uses threads and requires shared memory. This is fairly easy to implement, but you're limited usually to one node on an HPC machine. So this limits the overall scalability. Also touched on MPI. So this uses processors, can run on pretty much any machine, and the messages are spread over the interconnect, so you can use multiple nodes and all processors within nodes. It's harder to implement, so you have to worry a lot more about the message passing and communications, and dividing the problem up, things like that. But usually you get better scalability because you can use multiple nodes. And then MPI and OpenMP, MPI plus OpenMP, which is a combination of these, where you use shared memory within a node and messages passing between nodes. This can have advantages over using pure MPI, such as reducing the amount of messages and reducing the memory requirements, but not always. It can actually perform worse than just using MPI on its own. And then we covered a bit about GPU parallelism. Okay, I think that's me done.
Cool. Thanks very much, Holly. So
going back to the exercise.
No, I think that there's a break for now, and we'll return to the exercise at in about half an hour. If anyone has any questions about the exercise or things like that, I'm still on hand to answer any questions you might have. Yeah, that's it. Otherwise, we will see you again in 20 minutes. So at 10 to 3 UK time, 10 to 4 European time, Central European time. And I hope you can make the conversion for if you're not in either of those. Okay, everyone. Well, I hope that you all had a nice break. And following this break, we're going to move on to our second GROMACS practical. Let me start by sharing my screen. Yes, that should be okay. I'm going to do that so that you don't get too much of the tunnel. Cool, everything's hidden. So during the break, I collated all of the times that people had said, or most of the times that people had said. Some of them seemed a bit off, so I didn't include them. For instance, this time here, I'm not sure whose that is. That's absolutely fine. It just looks like it's a single core result rather than a 16-core result. I collated everything, and someone had pointed out that I probably made a mistake, so I got rid of my 512 results as well. Don't worry, everyone makes mistakes, including me, definitely loads of times me. And got this nice little table and started playing around plotting it. So these are the wall times that we got. Let me set log scale there because it's always a bit easier to see these things with log scale on. I'm plotting everything in my local system, so on my laptop, which is why you can see more colors than you would on ARCHER2. Yeah, and so what we're seeing is the wall time seems to stay the same between 1 and 2 nodes, and then starts to decrease what seems like linearly. If we take a bit more of a look at this, we can look at the performance, which will be 298 divided by the second column. Sorry, this is the speed up rather than the performance. And you can see the speed up is not particularly, well, let's find out, versus f of x equals x. There we go. Our speed up is not, it's quite poor from 1 to 2 nodes, from 1 to 2 cores, but then past that it seems quite good. So actually if we were to shift that a bit and do that as f of x equals, well, actually, we can even do that. I think we want to shift to x minus 1. If we started at 2x, you can see that the line is actually a lot closer and seems a bit better. And then finally, the other thing that we can look at is the performance as measured by GROMACS. GROMACS uses nanoseconds per day. And if we plot nanoseconds per day, and we don't really care about that bit, we can see that the nanoseconds per day increases much better, which suggests that maybe one of the wall times for this might have been wrong, or maybe this wall time was wrong. I wasn't able to recreate either of those, so I'm not sure which it is. But if you look at the performance all of a sudden and compare it to our simple line, you can see that at the start, the slope of the performance is roughly equivalent to the slope f of x equals 1, which means that the performance is improving nearly linearly. And then all of a sudden at around, that looks like 16 cores. At around 16 cores, it starts to die out a bit and get a bit noisy. So that's the results that we got as a group. And I find them quite interesting. I'm going to stop sharing my screen and start sharing just this bit. Nope. Yeah, that bit. So the second practical, the second GROMACS practical, here it is, we'll now start looking at using hybrid MPI and OpenMP jobs. And we've already touched on this, but to run a hybrid MPI with OpenMP job, you need to do a number of things. Instead of always setting the number of CPUs per task at 1, you'll now need to increase or change the number of CPUs per task to the number of threads you want per MPI task. Per MPI task. The other thing to bear in mind is that the product of n tasks per node times CPUs per task must always be equal to or less than 128, or Slurm will be unhappy. So that's how you run MPI jobs. And you can run, one last thing I wanted to mention is that for hybrid MPI OpenMP jobs, you need to start considering the ARCHER2 NUMA regions. So each ARCHER2 processor, and this is processor as in set of 64 cores, has a number of NUMA regions. There are 4 NUMA regions per socket, and that means for a total of 8 NUMA regions per node. What's a NUMA region? A NUMA region is almost an extra layer of memory, which is faster to reach by cores within that region than it is by any other core. And that can, if you distribute jobs appropriately around NUMA regions, you'll be able to get a bit of a speed up. You'll see a bit more about what I'm trying to say by carrying out this exercise, and also I'll give the results towards the end of the session as well as tomorrow. But bear in mind that essentially, if you're wanting to get the best sort of performance, you want to consider NUMA regions, and you want to divide your jobs in chunks of 8 cores. So 8 MPI tasks with 16 OpenMP threads would be 1 MPI task per NUMA region and 16 threads per NUMA region as well. If you go to 16 MPI tasks for 8 OpenMP tasks, then you're using 2 MPI tasks per NUMA region, and that will still be faster than other subdivisions. But you'll see that in a sec. So for this tutorial, the idea is the same as the last time, except I want you to all use as much of a single node as you can, and run jobs that have MPI ranks and OpenMP threads. So 128 MPI for 1 OpenMP thread, which is similar to what we ran before, but then also 64.2, 42.3, 32.4, etc., 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 and then sort of tell me what wall times you get and what performances you get. I've again made a table here, and someone's already started filling it in. Thank you very much. I've again made a table here where it shows the number of tasks per node and the CPUs per task, just to make it a bit more obvious what I mean here. And I wanted to mention that I've copied a new Slurm job in TA017 work/TA017/shared/Gromax practical / it's called gmx sub2.slurm, and that I'm going to share my terminal, I think, because that'll be useful. Boom. There we go. So you can find the information there, or the submission script there. And what I've done is, or what I've done that's different in this one is I have, let me see, it's going to be this one, I think, I hope. Nope. Sorry, a moment while I find, that's the one I am. Cool. While I find the correct. Yeah, there we go. And what I've done in this particular Slurm script is, so it's exactly the same as before. I've put both QoS standard and both the standard with our reservation and the short with the short reservation. If you want to use one versus the other, you need to remove the spaces for one, add the spaces for the other, and you'll need to change tasks per node here and CPUs per task. And the final thing is I've set it so that the thread number is automatically set to whatever you've set CPUs per task. And I've set it so that when your md.log file will automatically be saved as the number of tasks you've run .log. You can change those if you want. You'll need to copy it to your local directories to do so. I don't want to save that. And the final thing I wanted to touch on is I would strongly recommend that you do not do, there it is. I would strongly recommend that you do not do the 42 tasks and 3 CPUs per task, or the 25 tasks and 5 CPUs per task until you've done the other ones, because they can take a very long time because you're spanning NUMA regions, which means that you've got longer communication times. In fact, I think this one takes over 10 minutes, so I'm going to get rid of that one. And yeah, and as before, if you could put in the answers that you get, that'd be grand, and hopefully I'll be able to collate them into something nice. At this point, I think I've said everything you need to know for the exercise. Please let me know what questions you have, and I will come back. What time does this session end? I cannot remember. I will come back at around 15 or 20, 10 or 15 to discuss the results. Okay, well, thank you everyone for filling in so many of the performance data that you've been getting. So it's quite nice that overall we're getting very similar results. I suspect that this first result here, whoever uploaded this result was using a single task per node and a single CPU per task, rather than 128 tasks per node and a single CPU per task. But everyone else is getting times which are roughly in the 14.3 region. For wall time, and performances which are roughly 120 nanoseconds per day. You'll notice that if you increase the CPUs per task by 1, so that you end up with 64 tasks per node, each having 2 threads, you can decrease your wall time by a fraction, about 1/7, to roughly 12.5. And you can likewise increase your performance by about 1/7 to 137 nanoseconds per day. Now, I'm the only one who did this one, and that makes sense because it takes forever to run. But if you run on 42 tasks, each with 3 threads, then it will take 162 seconds, which is ridiculously longer than any of the things seen before by about 1 order of magnitude. And likewise, the performance will decrease by that same order of magnitude, at least to 10 nanoseconds per day. And the most fascinating thing is that not only is it way slower than the 64.2 runs, it's also way slower than the 32.4 runs. Now, what's the reason behind this? Well, it all goes back to what I was saying before about the NUMA regions. So please put your hands up, by the way, if you want me to go into a bit more detail and take some time explaining what a NUMA region is. Otherwise, I will just very briefly give an overview of this. But because the nodes are split into 8 NUMA regions, or the processors on the nodes are split into 8 NUMA regions, and each NUMA region has 16 cores, when you do jobs that are multiples of 16 or submultiples of 16, then your jobs will be placed in such a way that communication between the cores, or your tasks will be placed in such a way that the communication between these tasks will be sped up as much as possible. Now, if you've got a number of 3-thread tasks, then there's no way to fit them all on your cores such that all 42 of the processes you're trying to run will be in a single NUMA region. There will always be the occasional one which will overlap from one NUMA region to the other. And at that point, the communication time between the threads in that process which overlap the NUMA region, that communication time increases dramatically. And I didn't expect this dramatic an increase, but hey, there are the results. If anyone wants to run these overnight to make sure that I've not messed this up, I'm pretty sure this is right, but please do check. that's why you get such a huge drop-off by going to 42/3. You'll also get a tiny drop-off from the fact that the total number of cores you're using is 126 as opposed to 128. But frankly, what's 1/64 compared? 1/64 difference does not explain a factor of 10 increase in decrease in speed. Then the 32 cores, again, are way better than the 32 4s are way better than the 42 3s. However, they're still significantly worse than using just 2 threads or even just using 1 thread. So clearly, we've already passed the peak at this point. And I wasn't able to run the 16.8, but the 8.16 that I ran took some 124 seconds of wall time, and you can see that as soon as you've passed that peak, which for this particular system on ARCHER2 seems to be at a 64 tasks each with 2 threads, once you pass that peak, your performance starts to drop off very, very quickly. So hopefully you found this interesting. Please, as always, I'm happy to answer the questions that you have. And other than that, I think we're a bit ahead of schedule, but considering that this course is now nearly at the end of day 2, I'm sure that's not an issue if we just move. I'm sure none of you will mind if we move straight on to the compiler's lecture. Also, it's a nice change that I'm ahead of schedule rather than behind schedule. So unless you have any more questions you'd like me to answer, I will pass over to Holly to continue and talk about compilers.
Hello, everyone.
Hey, Holly.
Here comes the tunnel. Okay, so I'm going to talk about compilers for a bit. So this will give a bit of an overview of what actually happens when you compile some code. Yesterday, we compiled Hammer as part of the exercise. So yeah, we can kind of go into what actually happens during this process and some things you might have noticed. And then we'll just let you know some things you should be aware of when compiling your code. But this will kind of be a bit of a brief overview. We won't go into too much depth because compilers are very complicated. So yeah, here's the outline. We'll cover what does compiling mean, so what actually is happening when you're compiling your code. What's the anatomy of a compiler? So this will be broken down into a few stages. What optimizations can a compiler do on your code to try and improve it and improve the performance? Can the compiler parallelize my code? So can the compiler actually do stuff to make your code run on multiple cores and run parts at multiple times? And what are the differences in the different compilers? So you might have heard of a few different compilers that are around. What are the main differences between those? So this is an overview of compilers. HPC programs are usually written in high-level human-readable languages. So if you're ever working on an HPC program or writing your own code, usually the big ones are always written in Fortran, C or C++. So GROMACS, I believe, is written in C++. CPGK, which would be the exercise tomorrow, is written in Fortran. Yeah, all of them are pretty much written in these 3 languages. And these languages are all languages where you have to compile to generate an executable. It's rarely something else, such as Python or Java. These aren't really used that much, though they are becoming slightly used in some cases. So yeah, you start off with this kind of high-level human-readable code where you have sets of functions and things that you can read and understand what you're doing. And then compilers basically turn this into machine code, which is what the computer understands and can operate on and know what to do. So it generates a set of instruction sets, such as sort of loading data, writing data, things that the computer understands. So compilers convert this high-level source code into this machine code. It can also incorporate functionality from external libraries. So I touched on this briefly earlier, but you have libraries that all kind of may have sort of the same sort of function or idea behind them, such as linear algebra, and these can kind of be incorporated. So these will be written to be performant and useful, and then these can be incorporated into code to the compiler stage. Compilers will optimize the code produced to try and make it run as fast as possible on the processors, so they know a bit about the underlying architecture as well. So what does actually happen when you compile? How does it actually work? So compilers flow, it's broken into these different stages. This is quite a simplified overview of what actually happens. It's actually a bit more complicated than this, but for the sake of this course, we'll break it into this compile stage, where you have the source code and it's converted into machine code. And here you get object files, so these .0 files. You might have seen loads of these being produced yesterday when you compiled Hammer. So these are the machine code. At this stage, libraries can be incorporated, and then the final stage, these are all linked together. So all these object files are linked together to produce your application, or your binary file, which you then go ahead and run. And this is the thing that you put in your srun command, and then this is run on the back end. So first stage is the compile stage. This transforms this source code into machine code and produces the object files. There's usually one object file per source file. So you might have a file called something .c, and then the object file will be something same name but .o. And then this is usually consists of a number of substages. So we're not going into these substages right now, but there's a few different stages involved in this compile stage. And optimizations are performed at this stage. So this is where the compiler tries to optimize the code to make it run as fast as possible. And yeah, as mentioned, libraries can then be incorporated when you're linking. So libraries provide some kind of common functionality across the different programs. So for example, we have low-level libraries such as file system access, and stuff to do with like I/O, which is usually not that interesting. You have numerical libraries such as those involved in linear algebra and Fourier transforms. These are more sort of incorporated into applications such as CP2K and VASP and large solid state or chemistry applications. And then communications and parallelism libraries, which I mentioned earlier during the parallel models lecture. So MPI and OpenMP. So these are libraries that deal with parallelism and communications. So the compiler combines the code into these libraries, the code generated from the user's program to produce the final executable. So this is done at this linking stage here. So you can, in a static link, this is what actually happens. So it's combined into the executable at compile time. However, you can also have linking at runtime. So this is known as dynamic linking. So for example, when you have shared libraries. Yeah, and then this link stage. So the object files are combined together and linked to form this binary file. And then, yeah, including all the library code, that's also linked. And as mentioned, you have static linking. So all this code is combined into a single executable at once during the compilation, or dynamic linking. So the libraries are not combined into executable, but instead they are called and executed dynamically at runtime. So maybe you might have seen sometimes if you run a code and it can't find the libraries at runtime, So if you run something and then it complains they can't find lib something, this is, yeah, it's trying to dynamically link the libraries, but it can't find them. So yeah, compiler optimizations. So as mentioned in this first compile stage, the compiler does optimizations on the high-level code to try and make it perform better. So we'll kind of cover what they do and when should or shouldn't I use them. So yeah, it tries to alter your code so that it will run more quickly. So there's lots of different levels of this. So at the high level or the assembly code, and that can include reordering of operations. So what it's basically trying to do is improve the code. So it might try and take things, run things in different orders, for example, if it makes sense for accessing memory in the right order. It might also do some things to the loops that you have in your code, such as unrolling them or fusing them. So unrolling is taking them apart, fusing them is putting multiple loops together. And then other things such as inlining functions. So this means like pulling the code out of a function. And all these things are designed to make it easier when the code runs, to make it run more quickly, basically. So if you're accessing different parts of variables like which are close together in memory, it's a good idea to access them in order, so that you don't have to keep reloading things from the cache or different cache levels. So it's all a bit complicated, but yeah, the compiler does it all automatically. So these are called optimizations, but it's kind of a misnomer. So resulting code is never optimal, and that it's the best it could be and the most optimized. So it kind of just does a predetermined sequence of transformations that's known to give performance gains. So it's not really like measured. The compiler is just kind of guessing based on what it knows to try and improve performance. So there's not any iterative process, and there's no attempt to quantify the effect of the transformations. So not usually like stages, it doesn't quantify. So yeah, here's some common optimization strategies. So loop index reordering. So this might be just basically reordering the indexes in the loop. So calling them and accessing them in different orders to match the memory layout. So these can be done as long as it doesn't affect the result of the code. So it can sort of move things around as long, and the compiler will know that the overall result isn't changed usually. Loop unrolling, so we do multiple loop iterations at once. Changing to use fast mathematical operators, for example, mathematical functions such as square root. You can use different mathematical operators which are faster. Function inlining, which is avoiding a function call by kind of pulling out the code from the function, and operation reordering to allow cache to be reused. So reorder the operations, and then it prevents having to load some cache like suboptimally. So you want to reuse the cache that you have currently loaded rather than loading different things, and yeah, because loading stuff from cache takes time. So here's an example of different compiler flags. We have Cray, Intel, and GNU compiler flags. So at the moment, the only ones that are relevant on ARCHER2 are Cray and GNU because it's an AMD machine. We don't have the Intel compilers. I'm going to gloss over these a little bit. Some of them are more important. So if you look at the suggested optimization for all of these, that's usually useful. So this is the kind of suggested optimization to get good performance without sort of over compromising. So usually the code will run correctly and everything will be fine. So this usually uses O2. So you have different levels of optimization, O2, and then you can have O1 and O0 as well. and O3. So the number, higher the number, the more optimized it is. So O2, you can see here that different things are done at different levels. So vectorization, for example, on Cray, this is done at O1 and above, and Intel it's done at O2 and above, and O3 for GNU. And then here, aggressive optimization suggested. So this is using O3 here, and fast on Intel, and O-fast for GNU. So this is just some things to be aware of if you're ever compiling your code. So when should you use optimization? The answer is always. If you don't use optimization, compiler optimization within the code, it will definitely run slower, almost certainly run slower than when you're using optimization. So for example, you could compile something using O0 and really take out all the optimization, and it will be really slow. So you should always use the performance gains given by optimization. You can switch off optimization if you're debugging. So if you're debugging some code and you want to know that the order you've written it is the order that the operations are happening, you might want to switch off optimization completely so that you can work out what's going on, and if you have like an error or something. So in this case, you could compile with like O0 and turn off all the optimization. And if you suspect the call is in a problem, you can turn them off gradually. So maybe go down from using O3 to O2 and see if your problem still exists. All good compilers allow the specification of a range of optimization levels, so you can turn off gradually, as we've just seen in the previous slide, where we had the different optimization flags for the different compilers. So compilers and parallelization. Can compilers actually parallelize my code? So this was touched on a bit earlier by Arno in the hardware lecture. So compilers can produce parallel or vector instructions. So this is making use of SIMD. Basically, you're loading multiple data at once and then using a single instruction on this data, which is available on the core's floating point units. So you're taking multiple data and operating with a single instruction in parallel at the same time. So yeah, this is like a parallel instruction. However, compilers can't actually produce high-level parallelism for scaling on multiple nodes or cores. So they can't go away and kind of work out how your code can be parallelized and which bits can run in parallel. For example, they can't decide if you have which parts of the code can be parallelized. The data parallelism is easy to automatically do than task parallelism. So it doesn't have like the overall holistic view required to produce this level of parallelism. So it doesn't really know how to subdivide the problem on a higher level. Attempts have been made, but with limited success so far. So now cover the different compilers and what the difference is between them. So compilers have different standards and implementations. They usually implement behavior specified in agreed standards for the languages. These kind of standards have changed over time. And yeah, they don't cover all cases, and there are ambiguities. So whether the standard is not clear, it's up to the compiler to architects to select behavior. So you have sometimes differences between different compiler implementations, and this can kind of facilitate or hinder different optimization possibilities. You have some compilers which are open source, for example, the GNU compilers, and other commercial compilers such as Intel. These Intel compilers can take advantage of detailed knowledge about the hardware behavior. So you tend to run, if you run Intel compilers, using Intel compilers on an Intel machine, and yeah, usually they can gain performance or optimization because they have more knowledge about the hardware. So to summarize, compilers are hugely important to HPC. They're required for pretty much building most of the applications, seeing as they're all written in C, C++, and Fortran, and these all need to be built. They can provide significant performance benefits. So a compiler can absolutely optimize your code, and you should always use optimizations. There are some caveats to this. And yeah, it's important to be aware of the difference between different compilers and whether your code requires a specific compiler. So if you've got some code and you need to build it on a machine, you should always check the available compilers on that machine and check the recommended flags for that machine, which will be found in their documentation, and then look at the documentation for the code you're trying to compile. So yeah, you need to check what are the suggested settings, what are the suggested flags, and really use this. So that's it for my talk. Are there any questions? No. Okay, that's related to the course. I think we're doing a summary and a roundup now.
Yeah, that's right.
Cool.
So thank you very much for that, Holly. I will share my screen. Cool. Yes, great. Well, thank you very much, Holly, and thank you everyone for coming for this second day of the course. Like yesterday, I would really appreciate it if everyone could take a moment to tell us, as a review of today, what you felt we did well today, what you felt we could have done better, and if there's anything specific you'd like us to focus on tomorrow, what you would like us to focus on. We really did take into account all three of the things you mentioned yesterday, and have tried to focus definitely on the parts that you asked we focus on. So if you could do that in the course Etherpad, that would be brilliant. I've put a link in the chat. And what was I saying? Yeah, and I quickly wanted to say, well, what have we looked at today? Today's been quite a busy day, and as hopefully you'll have noticed, a much more hands-on day. We talked about how to measure parallel performance, followed by a quick practical where you were measuring parallel performance. Arno and I gave a description of the computational building blocks, what makes a computer, what makes a supercomputer, what are the Legos with which you can build your computers and or supercomputers. We then had a GROMACS practical where, again, you were performing some benchmarking. The benchmarking here was entirely looking at the strong scaling, i.e. how much faster a system runs as you increase the number of cores. Before a lecture on parallel programming models by Holly, there was then a GROMACS practical looking at hybrid OpenMP MPI codes, followed by what's just finished now, a lecture by Holly on compiling software. So for tomorrow, tomorrow is also going to be intensive from a practical point of view. We'll start off with a final GROMACS practical. Then Arno will be giving a talk about pipelines and workflows. This is very often used by bioinformaticians and quite important in the life sciences, so should be interesting, and definitely for anyone doing molecular dynamics, even though this is not molecular dynamics related, it's still a different way of thinking about problems and definitely worth coming to. And then after that, we will be, the primary practical for tomorrow will be a two-part practical using CP2K to run QMMM simulations, so quantum mechanical and molecular mechanical simulations, so hybrid of classical and quantum simulations, which will be run by Holly and will be very interesting. And then we'll finish off by talking about the future of HPC. We've already hinted at this before, but we'll discuss how the HPC landscape is changing, the move over to maybe more GPU-dominated machines, the increase in interest in shared memory systems and things like that. And to finish the day, we will discuss what the HPC landscape is in the EU and the UK, and where you can find out more about high-performance computing within the UK and within Europe, how different high-performance computing centers are ranked and what these ranks means. And we'll finish off with a review of the course, mentioning where you can go from here, talking about further training opportunities that are available through PRACE, through BioExcel, and through EPCC, and finish off by doing what we refer to as a bootstrapping session, where we will happily answer any questions that you might have for us that we didn't cover during the course. So with that, unless Arno and Holly have anything else to say, thank you again, everyone, for coming today. It was great to have so many of you show up again today, and we look forward to seeing you tomorrow. And I hope you all have a good evening, rest of the day, and see you tomorrow. Oh, and just quickly as well to mention, if anyone wants to carry on with the GROMACS practicals, I'll be around to answer any questions. There was quite an interesting series of questions about using OpenMP, which I will talk about during the GROMACS tutorial tomorrow.